What? 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 Wacky Wednesdays.
What's up, everybody? What is happening? How's everyone doing this morning? It is Wacky Wednesday with some 20 points, 200 points max today. The test is out there. How is everyone doing? Let's see how everyone's doing in the chat. Tell me how you're doing this morning. How are you doing? Anybody? Good. How am I? I am doing great. The tests are out there. Some people in 474 have taken their tests. They're doing quite well. We'll see how everyone's doing. Remember, the take-home's due Friday night. The test is due Thursday. I can't even think. Thursday by 2 p.m. So you've got two responsibilities right now that are pretty major. Now there's assignments and stuff like that. Um, um, I might have made the midterm too easy. Well, maybe I made the 474's midterm too easy and I made their take home too hard. We'll see how all the grades go. Remember, I'm not going to let the average be below a 75. So, let's say I was telling people on Discord last night, the first time I ever made an online test, I was like, this is too easy. And then the average was like a 40. But they're like, oh no, everyone's like, oh gosh, no. But so far the 474 individuals who have taken it have gotten A's. There's, I think, only two people have taken it and two people have gotten A's. But people who take it are more likely to be like, okay, I got this. Like I'm good to go. So on the take home, it can be like general stuff. Usually email them to me. I don't really explain how to do anything. I kind of rephrase it and I kind of say like, here's what you're looking for. So I don't really like explain how to do it. I don't like say, oh, you want to run this function or here's where your error is. I don't really go into details on like how to fix things. But if it's like, I don't understand what this is getting at, I don't know what this is looking for, I kind of say, oh, well, you want to find, like I was telling someone for 474 last night, I was like, your objective for this one is to make a data frame. And if you notice, it says it wants 2 columns and 4 rows. So think about what your rows would be and what your columns would be. And you want to store this data frame with these values in it. And I was like, there's a few ways to do it. I was like, a homework has one way to do it. And so now they're like, oh, a homework has a way to do. I mean, the hints are so small that it really doesn't, it doesn't. The best I can do is often rephrase them. But you can. A few people have asked me questions from about the 320. I guess I can say it like the one that wants you to find correlation is looking for Pearson correlation. That's been asked, I think, 3 times. So the one that wants correlation is Pearson correlation, and then the one that wants R squared is, I can't say exactly like where it is in the output, but there's only one R squared. Like R squared is R squared. And you'd be like, wait, but is it this or this? Double check the notes. Because if people are like, well, is it this or this? And I say it's R squared. Because in the output, there are things that like say things R squared and another R squared, but there's only one that is R squared. And I think I make that clear at the end of Monday's lecture. Well, that's a big hint. I go through that output and I say which one's which. So those are the kind of hints I give. Like it's like, well, I don't want to be too specific. Am I allowed to ask stuff? Am I allowed to ask what kind of stuff people are putting on their cheat sheet? See, I'm iffy on that one because I'd hate for someone who's like taken it, like that. You don't want to like ask people who've taken the test, like what's on the test or like what I should put on my cheat sheet. I'd maybe, I'm iffy on that one because, then that's like someone will be like, oh, you should definitely have this on there. Cause I tried to come up with like, I think came up with like 60, 70 questions and then they rotate, like different people get different questions. I tried to keep them all about the same difficulty. It's really hard building tests. And I probably over the last 2-3 days wrote 150 questions across both classes. And so my brain just got like fried with writing questions. And so I would probably, if somebody is saying to you, yeah, I'd probably just like, yeah, no, that's good. Yeah, and I was saying to people that the way I'm building the tests is one, the Kahoot is an excellent way to study for the test. The Kahoot I built after making test questions, so it's literally geared towards what I was writing. Also, the practice test is a really good example of, I think, how you'll do on the actual test. So, yeah, I think Connor's on a good track right there because when you look at what's in the notes, I literally was going through the notes and like being like, okay, what could we do here? Like, maybe a question for the final would be something like, which of these is the proper notation for the way we write the regression equation. It could be a multiple choice and it'd be y hat equals b0 plus b1x. Like that's something we should know like that. So when you think about the things right here, or which of these notations identifies the slope right here, which of these on the screen, first 100-point question, you get up to 200 points today, which of these identifies the slope on the screen? Which of these is the coefficient of the slope, I should say? It's still the same if you say it's the slope. Which of these is the coefficient of slope? Yep, Dennis, B1, 100 points right there, B1. So B1 is the coefficient of the slope, X is the variable. So be careful because X is the variable, B0 is the intercept, and Y hat is the estimate. So really good stuff right here. We're already jumping into a little bit of review of the lecture. But B1, 20 points, everyone else. Dennis, 100 points right there. Boom. B1 is the coefficient of the slope. B0 is the coefficient of the intercept. X is the X variable. We'll give it a name, whatever it is. And then Y hat is the predicted value. And be careful. It's technically lowercase b1. So beta 1 is the truth, which, do we show the truth in here anywhere? Where's the truth at? There it is. Here is the truth. And we really don't show this off that much. So beta 0 is the true intercept, and beta 1 is the true slope. I probably won't do a question like on tests like that, because that's really like theoretical. Like they're like, it says in the notes, those are holy quantities that we never know. And when we make a confidence roll, those are what we're trying to estimate. We're trying to estimate the true slope and the true intercept. So, and we never really know them because all models are wrong. Like they don't even really exist. It's just a theoretical idea that there might be a truth to this model if we had all the data. So you'd have to have all the data, which a lot of times is virtually impossible for any sort of regression. 200 points, Sylvia. 20 points, Sylvia, right there. Good question. 200 points. And so any other last questions about the test right here before we get started? Last time the notes were updated. I need to update the notes. Last time notes were updated. It seems like 2016 was yesterday. Gotta drink more Red Bull. What's up? I don't know how to drink Red Bull. I think we're good to go. So my big suggestions for the test are: 1, go through the notes, make your cheat sheet front back. 2, do not have anything out writing during the test. Do not be writing during the test. Everything is there on the screen for you. You've got your graphing calculator. Please tell me if there's any issues. There was already one issue on the 474 test where I had 2 answers with the right. I had a question with 2 right answers. Well, hopefully that's changed. So the thing is everyone was selecting the wrong answer. And I was like, oops. So I went in and changed that. So please tell me if there's any issues with your grade or anything like that. Please tell me any issues with the question. Once again, don't tell people, like, once you take the test, don't go tell people like, hey, there's this. 2, don't write things down. It's just like any other test. Like if you're in a section of like a class that has 3 sections, don't go then to another section and be like, hey, this was on the test and this was on the test. So I think we're good to go on the test. Review the notes, take the practice test, do the Kahoot, and come to class, and you should do pretty well. That's my goal. If you're coming to class, if you're doing the things you should do, if you're doing the assignments, I want the test to be pretty, like you get an A or a B. So we'll see how everyone does. Once again, once you take the test, don't worry about emailing me, because either the test's going to go off like I think it'll go off, maybe it'll go off better, grades will be really high, or grades could be really low. If grades are really low, there'll be a curve. So, once grades are finalized, once I know what grades are, then definitely say like, hey, Brian, my grade was this. What can I do? How do I get back on track for a B or an A? What can I do? So, because I know it's really unfortunate. Let's talk about one really quick thing real quick, is that variation. I've seen this. Let's hop to the main screen. What's really interesting, I'm so small from yesterday. We're playing the Kahoot. So what's really interesting is that if you were to take a whole bunch of tests, you have a kind of like average that you would do. But there's variation in that. And maybe you're a A- student, like you have an A- knowledge, but there's variation in the test and like within your abilities. So you're not going to always get the same grade. So all of a sudden, a student who's working really hard, who's an A- student, could all of a sudden get an outlier and score down here and maybe make something like a like a 78. And this is like a really hardworking student. Like this is like the 1 in 300 test. So I guess it'd be even less than that if it's on the third standard deviation. But this is like a big outlier for them. And this happens. Like you take enough tests during your college career or your whole academic career that every once in a while you're going to have an outlier. And it's not that you didn't know the material. It's just that, you just had the subset of questions that, I picked the questions that you didn't really know. And it's going to happen to a bunch of people. And I think I notice it more because I test hundreds of students a year. If you just look at 1,000 students a year, which I test about 1,000 students a year. If you look at all the tests I do, I test about 3,000 students a year, like with the multiple tests. And then the 3 standard deviations, secret, let's do this right here, secret 100 points. What % of people would you expect to fall below 3 standard deviations? It's kind of a question from yesterday, a good review question. What % of students would you expect to fall at the bottom end of the below 3 standard deviations below the mean? Very close, Brad. You're on the right track. Brennan even closer. Brennan's even closer. Alex pretty much rounded down. Alex's answer, there go Henry, 100 points Henry, you're right. Henry's right. Because this leaves this amount on either side right here. So that is how that's, and it's on the other side too. Sorry, my scribble is so bad. But there's, if you look at this, this would be 15 students out of 1,000, or out of 1,000 tests, 15 of them will, and I understand because when this happens to you, when one of my 15 students out of 1,000 gets a grade that's like, whoa, wait a minute, I studied hard and I got like a C, and like they really knew the material, like they're like, no, like, and don't worry, like I get this, like I helped my friends study, like I was helping them do this, and they got an 86 and I got a 78, and you're like, I was telling them, I was like explaining it to them. Maybe your friend was, above the mean and you were like their mean. So they were above, your friend was above their mean and you were below your mean. So it just happens. It's variation. And that's what statistics is all about. And I totally understand it because like, it makes no sense. It's just, it's random. They're not going to get me for that. If they get me for that, that'll be insane. There's no way they couldn't have content ID'd that. You take that. Crab Rave will be back. Let's hop back right here. Thank you, Crash Bandicoot person, for not content IDing us. That is transformative. That is transformative right there. Okay, so we're good to go on the test. We understand how variation works. We were literally doing a quick review of confidence intervals right there because 68% of our data is expected to be in 1 standard deviation or standard error, 95 within 2, and 99.7 within 3. 68, 95, 99.7. I also want to give a big shout out to the Discord. We had a really good talk on the Discord last night. I think Sylvia was there, Dennis was there. Correct me if I'm wrong. I think Sylvia was there. I think in the chat and stuff. And we had some 474s there. We had Andrew and Vedrina. And we had Alex there. And so we had some really good kind of working on stuff in the Discord. And I think the Discord has been working together. Yeah. Oh, no worries. Yeah. And so we were able to, Dennis was really great at asking the questions via he would ask them in the voice chat, and that way you could hear the voice chat. So don't worry. You can always, ask questions. You can listen in, and you guys are allowed to work together in the Discord to get together and to just have the open rooms and be like, hey, how do you do this one? Or like, can you explain to me the theory of this? And it seems like it's working really great. Like 320 is really doing some great stuff. And we're going to try to get 474 more active in it. And we're going to see how it goes with building the community there and get everyone to work together. So once again, check out the Discord. Big shout outs there. If you're confused on it, please email me or email Dennis. Dennis has been a huge help in that. And we're just trying to build a really interactive community that you can just, on your phone or on your computer load up anytime. So you can just like hop in and be like, hey, I'm just here to do some work. And people are like, oh yeah, well, let's talk about this question. So just like basically you have Stat Lab anywhere at any time, which I think is really cool. So, for 201, we have Stat Lab, but I'd like it if you could just be like, hey, I'm jumping in. And then we might start even working to getting our Stat Lab workers in there And maybe we could even try to get like 320 helpers, like 320 TAs, which would be awesome. Yes, we have TAs for 320. I'm going to either make a, yeah, exactly. Thank you, Dennis, so much for all this hard work. Yeah, so Discord can be a bit confusing, and then audio is always a problem. So Dennis is going to make some videos here helping out and showing how to do it. And from what I've seen, people who, I mean, maybe it's just bias, like it's response bias, like people who like Discord. Like if people didn't like Discord, they'd leave Discord. But especially with our Pokemon Go community, everyone was a little hesitant on Discord, and then all of a sudden we started doing Discord, and the abilities it has really took off. Like we went from GroupMe to Discord, and everyone was like, okay, Discord's way better. So that's got it. Are you ready for the next chapter that's going to be on the final? It is time. We're going to drink a Red Bull. Coconut Red Bull, and we are ready to go. Let's do this. So, we need to make predictions with our regression. And this was so complicated in 201 to make predictions. Like, so much time. Well, all we're trying to do is make predictions with this value right here. Now, there's two things that this can predict. It can predict the mean of y given some x, or it can predict an individual. Now, this is very, 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 very important for the interpretation on the final and on your homeworks. That either I want to predict, imagine Julio, which Julio said hey to me recently, and I really want him to make like a pep video for you guys to be like, hey guys, you got the final. I'll talk to him about that. He's doing great. Oh yeah, he emailed me. No, he sent me a thing yesterday because in his class, literally they were showing 68, 95, 99.7. So he was like, empirical rule. And I was like, yes. And so when we look at this right here, imagine the New York Yankees are trying to predict the batting average of a player. Would they be doing mu or y sub p? So you can type mu or p. So they're predicting the batting average for a player. Are they doing mu or p? Mu or y sub p? You can type mu or p. Batting average for a player. Which one are they doing? They're doing a batting average for a player. They are doing. Ooh, I tricked everybody. I mean, look at the two keywords. You can change your vote if you want. They're doing P. They're doing YP. They're doing an individual's prediction. So, and that's why I pause on these things, because this is like a big thing to know. So this right here is a prediction interval. We'll talk about that in a moment. It'll be on the screen. But Y sub P, 20 points if you attempted to answer that. Good job. Just follow along, write it down. That when we predict a particular individual, that is a prediction interval, and it's for one individual. But if they're trying to say for all individuals that maybe they're trying to predict the batting average for people who, they have a certain set of characteristics, like they swing the bat this fast, they do this. And if they're doing it for all of those individuals that share those characteristics, that would be mu sub y given x. So that's the mean of y given some x. It's the average. So this is the average given a certain set of characteristics, and this is for one particular individual. This will be called a confidence interval. And this is where it gets a little confusing. And this will be called a prediction interval. So please note down these key phrases that we have here: a confidence interval for the mean of y given some x, and we have here a prediction interval for the individual person or point. So when you think about prediction interval, think about like person. Predictions are for people. Confidence intervals are for the mean. So predictions for people, connect the P right there. The prediction is for the person. So a prediction interval is for a particular individual. Now you can make predictions you can do it for the mean, but prediction intervals are for people or things. They're for individuals. So predictions for people or things, individual items. So when does this come into play right here? Well, if we wanted to do a confidence interval for the mean, we could say the typical amount left on $20 bills at our restaurant. Like how much would we get on average? So we can say, okay, the typical tip left on a $20 bill is between this and this amount. But when you switch it to an individual interval, a prediction interval, it's like on this table that just left. So does everyone see the difference right here? This is the key difference. There's multiple examples, but I want to point to this one. When you do a prediction interval, it's like on the individual table that just left, what do I think I will get? That's a prediction interval. But a confidence interval is for tables that spend $20, on average, we would expect them to tip between this and this. So here's a confidence interval. On a table that spends $20, on average, I would expect them to tip between this and this. On the individual table that just left, I would expect them to tip between this and this. And I just gave some key stuff of what's going to happen. Which of these will be larger? The confidence or the prediction? Where would you have more uncertainty? Would you have more uncertainty, i.e. larger, in the average for a bunch or an individual table? The average of a bunch of tables or an individual table? Where would you have more uncertainty in your prediction? That's kind of the answer. You'd have more uncertain individual table, yeah. Because they could give you like a huge tip, or they could give you like a really bad tip. And so with an individual table, which is a prediction interval, the individual table would have more uncertainty, because with the confidence interval for the mean, you're going to average together the good and the bad tips. So you can see right here, a confidence interval for the mean is the average of what you would think for tables that spend $20. Like on average, a table that spends $20 is expected to tip between blank and blank amount. But this is the table that just left that spent $20 is expected to tip between blank and blank, which is going to be a prediction interval, which is a way wider interval. We'll see this here in a moment. Here's the mathematics. We don't need to know it too in depth. I might go a little quickly through this part, but it's very important we kind of understand what's going on right here. We've got here the RMSE. The RMSE is visualized by how far out your typical miss is. If this is my line, the points around it, usually I miss doing this in class, because I'll be like, someone make a line like this. Like I'll be like, make a line with your arm. And I'll be like, here's your typical miss getting larger. Here's your typical miss getting smaller. And I think we got some visuals on the screen in here, but you can see the RMSE. No, it's in the previous slides. I can pull those up real quick because it does a decent job of visualizing them. Open, simple linear regression part 1. Here we go. Where is that RMSE? The RMSE is right here. So here's what I'm talking about, those points being really tight. This is a very small typical miss. This is a very large typical miss. And this was used right here for the standard error of the slope, which is our uncertainty in the coefficient of the slope. So you want a very small uncertainty in the coefficient of the slope. And so now when we look at this equation, it still uses RMSE for our what? What is this right here? This is when we're trying to predict the mean, and this is our uncertainty in our what? Just wait, look up here. This is uncertainty, and this is what it's in. 100 points first person to kind of explain. Since this is uncertainty right here, not that. This, the standard error, just means uncertainty. I mean, it doesn't literally mean that, but I always call it that. This is our uncertainty, and it's in this. This is just put the words together. Uncertainty for your, what is it right there? And make sure to look at the top. It does say y hat right there, but then look at this right here. So that is our uncertainty of what? 100 points. Uncertainty and prediction of the interval. Yep, Brandon, right there. For the interval where, yeah, this is our uncertainty in the interval that we are using to predict the mean of y given some x. Brennan, 100 points. Perfect right there. Or Nicholas, too. I'm giving it both. Casey, Nicholas, Brennan, all get 100. It's our uncertainty in our interval that is predicting the mean of y given some x. Does that make sense? Standard error is just uncertainty, but be careful. We have standard error of our slope, which this is what? Someone explain what this means right here. The one I have highlighted, put this into words for 100 points. That is our what? What is this one that I've highlighted? Standard error of slope. What should you think of when you hear standard error? You should just change it to a new word. I put this on the test sometimes. I'm like, standard error is best described as this. And if you come to class a lot, you'll be like, oh, it's just this. Brian says that 1,000 times. Uncertainty of slope. Yep. And then the coefficient. Sylvia right there, 100 points. Yep. There we go. Standard error of our true slope. Kind of. It's because it's the true slope is what we're trying to estimate. So it's our uncertainty in the estimate of the true slope. To add more words. Well, no, good answers, everybody. Amazing answers. 100 points, everyone on the screen right there. Maybe get up to 200 points today. How about this one? This one's a trick question. I'll max you out 200 points, first person to say this one. because this is RMSE, which is root mean squared error. That SE is actually not standard error, but RMSE is also RSE. RMSE is also known as RSE, which has nothing to do with root mean square error. I mean, just the words, but it is the same thing. RMSE and RSE are the same thing. Like they're in R. Close, Sylvia. Close. And then change the words. So remember what topic we're talking about here. Yep, Emily. Emily gets max. And then what does that mean? What does that mean? So what does that mean? What does residual standard error mean? It's our what? And you're seeing it here visually. Well, there's a few things you could say. I'll say the one. It's the typical miss the residuals make. That's what the notes say, which is important to call it that. So the typical miss. Wait, how far off the... Yeah, Brennan gets max right there. It's about how far away the points are from the line on average. Brennan, that's an amazing answer, which I haven't said, but it's like your uncertainty and about how far they are away. Aaron right there gets max too. How far the points are. It's about typically how far away they are. Like the typical error the model makes. Stevenson right there. Boom. Steven gets max too. That's exactly what the notes say. Yep. And so it's your like uncertainty in the residuals. Does that make sense? Like these residuals have more uncertainty in them. And wait a minute. If the residuals have more uncertainty in them, the slope will have more uncertainty. Do you see the uncertainty in the slope where it's wiggling more here and it's wiggling less here? Like this slope is like locked down, but because there's more uncertainty in the residuals, there's more uncertainty in the slope in the second graphic. Does that make sense? Like the uncertainty in the slope literally looks like the slope's doing this, where this one over here has so little uncertainty, the slope's like boop, locked in because that slope has no uncertainty. So this is like our uncertainty in the estimates or the typical misses that the model is going to make, depending on what we have uncertainty in. Makes sense? That's what I want to see. So this is our uncertainty in the predictions. 100 points counter right there. Thank you for the confirmation right there. I want to always know what everyone's thinking. Whenever it doesn't make sense, be like, I don't know what's going on. You can say that in chat, and I'll be like, oh, let's explain further. So we have our standard error in the prediction of the mean of y given some x. We see here that sample size will decrease it. Once again, a bigger standard deviation of the x, which means our x variable has more variation in it, which is what we saw yesterday, will decrease it. And this is how far we are making our predictions from the mean of x. We will have the least amount of uncertainty when we are predicting at the mean of x. So if we are at the mean of x, like if our x value is at the mean of x, solve this right here. First person, 100 points. Solve this right here, just what I have highlighted. If we are predicting at the mean of x, what does this top thing solve out to? What does that solve out to? First person, 100 points. 0, boom, Grant, 100 points. Because Meal, 100 points also. We have right here that this right here, and Casey, there we go, I'm done. We have right here that this would solve to 0. And so that would have the least amount of uncertainty. The further out you go from the mean of x, and I'll show it visually, further you go from the mean of x, the more uncertainty you have. Do you see how this has more uncertainty? Because we're further out from the mean of x. The further you are away from the mean of the x, which here's the mean of the x, and this interval is the tightest, the further out you go, the more uncertainty there is in the interval. So that's literally what's happening in the graphic right here. So further from the mean of x, boom, we got that going on. And this is just showing you the standard error and how we use it, going out to standard errors. You know what's really crazy about this? I don't memorize this equation. I know how it works mechanically, but all we have to do is go outside of here and underneath the radical still, I believe, add +1, because guess what? The equation right here to do this, oh, it's before it, well, it's 1 plus. The equation when you do individuals, when you have the standard error, can't highlight today, when you have the standard error for predicting an individual, which is your uncertainty in the prediction for an individual, just adds this 1 plus. So what will this do if you add 1 plus? The uncertainty for an individual will always be water. Because you're doing 1 plus to whatever this is, all you're taking is just taking what this is and just adding 1 to it. And it's going to be square rooted and then multiplied by something, but you're still just adding to it. So you're going to do 1 plus. It's going to be bigger. Yep. So that's why your uncertainty for the mean of y given some x is always smaller. Here's the original one. And then we go over here and we see with the individual, it's always going to be larger due to this 1 plus right here. So it's the same equation. Everything right here is the same, but the individual is always going to have more uncertainty. And the notes go over that. Like the notes below here just kind of like walk you through everything I am saying about all of these equations. Once again, we are still just doing confidence intervals. And when you do your confidence intervals, you don't have to actually do them yourself, but we're still just going out usually 2 standard errors. So all we do is we take the prediction the line makes and we go out 2 standard errors. Now you might say, well, don't I have to do this? And the big thing people like to say to me is like, wait a minute, don't I need to know the exact t-score? Like, isn't 1.96 the exact t? No, that's the z. Sorry, I feel so mean. But the z-score for a 95% confidence interval is 1.96. But when it comes down to it, when we're using R, let's hop over here, we don't have to know the confidence intervals off the top of our head. We don't have to know the z-scores and the t-scores. We don't have to know them because R will instantaneously solve them for us. Let's go ahead and take a look at this right here. We'll go here and we'll load up library reg class. And reg class. And let's load up data survey 10. And then let's load up, this is the easiest model to make. Tilde weight, comma data equals survey 10. And so there's the linear model. We can visualize it. And what's really great when we visualize this, we got to make it, okay. It's because the visual, and you have to remake it once you do that. So what you're actually seeing right here, and this is very important in this graphic, is you are seeing the confidence interval right here. Remember how we said the confidence interval is tighter and the prediction interval is wider? See, prediction interval is the dashed lines. And actually, you can see where the mean, can anyone guess what the mean weight is for these students? What was the mean weight for these students? Someone take a guess. What is the mean weight? This is not a bad test question given this graphic. It's, see, I don't like it also. I don't know, 145, decent guess. I think it's going to be right about there. It's where this is the tightest. So I think it's a little above 150. I think it's like 157. So 153. Yeah, let's see. We can figure this out. We can go here to mean of survey 10 weight. And it's 155. And so it's wherever this is the tightest. So it's wherever that the tightest part is where it has the least. Nice job, Corbin, right there. Corbin, 100 points. 20 points everyone else, but Corbin, great guess right there. So yeah, it's right about there, wherever it's the tightest. That's where we have the least amount of uncertainty in our predictions. And does everyone see this is, we were predicting people's heights. So this interval right here would predict the average height of all individuals who weigh 155. Like we're saying, for all individuals who weigh 155, we would expect them to be on average this tall. But then if we use this interval right here, what would this interval right here be predicting for 155? For 155, this interval right here that I'm highlighting over the prediction interval would be predicting what? Explaining in words, for prediction interval for 155, this would be predicting what? The what of a what? So the prediction interval, it'd be predicting the height, but the what? It's predicting height, but the what for a height? This is for all individuals who weigh 155, would you expect the average height of them to be this? For all individuals who weigh 155, would you expect on average for them to be this tall? That's what that, no one's got it yet. This is where the confusion happens. So that this one right here that I'm looking at right now is the average height of all individuals who weigh 155. This one right here, between here and here, is what? I have to get with the answer. This one is an interval that predicts for an individual. So this is for an individual who weighs 155, I would expect their height to be between here and here. Does everyone hear the difference? For an individual who weighs 155, because I'm tracing down to here, so maybe that's about where 155 is at, I'd expect their height to be between here and here. For all individuals who weigh 155, I'd expect their heights to be between here and here. Yep, because this is a prediction interval, which is the wider one. This is a confidence interval for the mean, which is the tighter one. The prediction interval is for an individual's height. The confidence interval is for all people's heights when we're predicting the height for all people who weigh a certain amount. Do you hear the key difference between the prediction interval, which is the wider one, for an individual who weighs 155, I would expect their height to be between here and here. Yep. For an individual who weighs 150, great job, Brad, right there, 100 points. Yep, for an individual who weighs 155, I'd expect their heights to be between here and here. For all people who weigh 155, I'd expect their height to be between here and here. Like I'm 95% confident their height would be between here and here because it's like 95% confident. And you'd say, well, man, it seems like a lot of work to do. Well, all you have to do is we're going to go to data frame, and this is the longest part about it. And we're going to go here to weight, and we're going to store into weight a vector of something like, let's go here, 120. We'll put some weights in here that might be close to people's weights. 180, 220. Okay. So we put some weights in here. Maybe there's a weight close to your weight if you want to see what the prediction would be. And so we're just going to go here. We're going to go to predict M. Now, we're going to change this in a moment, but this will actually make predictions for everything in the data set. But let's actually go here and put in another argument, new data, and that one does not autocomplete, equals DF. There we go. So the person who weighs 180, which is kind of close to my weight, is expected to be about 5'10 or 5'9.5. The person who weighs 220, which is about the most I've weighed, is expected to be a little bit over 6 feet, which is 72 inches right there. But what about these intervals? We can put another argument. We can go interval. Really? I hate that this one doesn't have autocomplete. They need to fix their function. There we go. So now we have a confidence interval with this is for the mean. So this is for all individuals who weigh 120. I would expect them to be between this and this. And what we could maybe do is, you know what I'd like to do? Watch this. Let's go here to predict. And I wonder if Columbine, I wish it actually gave you predict DF. There we go. Oh, perfect. Now it's easier to see. Now it's easier to see that these are the predictions for these individuals, and these are the predictions for these individuals. There's their fit, which is their prediction, and so we could even change that. There's the lower and the upper, and this is the fit. Here's the prediction. Just to make it very clear, let's do that. Let me store this as total, and let's go here and go to names of total, and let's store in a vector real quick of prediction. Then let's store in lower. I don't know why it doesn't spell it out because it's not that long. Upper, and yeah, wait. We'll just call weights. I'm not gonna. Okay, there we go. And then let's run total. There we go. Much easier to look at. So we've got the prediction for the individual, the lower bound, the upper bound. Excuse me, prediction for the mean. And then if I want to do the individual, I'd go here to prediction. And these are in the notes on how to do this. And now we can get the individual's prediction. So this here, does everyone see that Brian, who weighs about 180, is predicted to be 5'9.5 with a lower bound of all the way down to 5'2.5 and an upper bound of 6'4.5. So Brian has and I am in this interval. This is the interval for an individual because it's a prediction interval. These are intervals for the average for all individuals who weigh 180. So this interval right here that you see is what we would expect on average for people who weigh 180. I'm 95% confident that the average height of a person who weighs 180 is contained in the interval this to this, where here I'm 95% confident that an individual's height who weighs 180 is contained in the interval blank to blank. Let's get some yeses. Does people understand the difference between prediction interval, which is wider, and confidence interval, which is going to be tighter? The confidence interval is for all individuals or all items at that given X value. Does everyone understand the key difference right here that we see visually in this graphic? And we also see good, awesome. So yeah, there's the prediction interval and there's the confidence interval. It's always tighter. And we saw the mathematics on how it works too. It's more important to understand how to do the code and stuff like that. But if you notice, once again, we like to make really good output. We like to show what's going on. And that's why I love code. It's like you can just fix it up. You can bind things together and be like, yeah, let's just put these things to this. And there we go. Let's do it. Okay. And once again, I want to point to why code is awesome. Because if I just go here and someone's like, well, I weigh 155 and I weigh 280. We're like, okay. There we go. New predictions. That's why we don't have to do stuff by hand in this class, is because if we write the code, it can just instantaneously do it. Better yet, I could probably watch this. Let's go here, value. Watch this. Let's go here to read line. Where's read line? And let's go to value. Oh, what is your weight? Let's ask people that. And let's go here to value, and then as.numeric. And then let's put it inside of here. And I think this will work. We'll cross our fingers. And let's go here to predict height. Function predict height. And it won't ask anything. We're going to go here and take this, drop this inside of here. We're going to go to this. We're going to go to return. And I think we've done it. Okay. So now if this works, I should be able to go to predict height. And I should be able to run it. And it says, what is your weight? And I say 180. Oh, I'm like 188 now. And there we go. That's it. I don't like that there's no space after this. I want there to be a space. So I'm going to fix that. But does anyone want me to predict? You don't have to put in your actual weight. But does anyone want me to predict your height? Does anyone want me to predict your height? Put in a weight. It'll predict your height. I could make better models. 220. Whoops, I didn't hit enter. There we go. Boom, 170. So I don't think I can put in a vector. You know, I wonder if I can put in a vector. Let's try here. 125 this is not going to work. This is not going to work. It's going to get mad. Yeah, it got mad. It said NA. It can't return because it couldn't make the table. There we go. 164 right here. So if you notice, this is really nice and easy to use. You can just, there you go. Cool, huh? There you go. Yeah, pretty interesting, right? So this is what we like to do with stuff, and this is what we do in 474 more often, is like make things into functions. My function has here a read line, which takes whatever the read line asks for an input. That's what read line does, is it asks the user for an input. And then I'm taking whatever someone inputs and turning it to numeric, because I think read line originally takes things as a character. Whatever you type into a read line is a character, but I'm turning it to a numeric. I'm storing it into value, and then my code just runs like before. So everything right here is like it ran before. So it just asks you what your weight is. It stores that to value. Then it makes a data frame of that value. It makes a model predicting it. We could even make but the model's, yeah. So the model's already made outside of this. It's not a good idea. This needs to, well, okay, we're not going to build the rest of the function. But yeah, if you run the code in order, it'll work. But the function by itself is not perfect yet. There's always, hey, Wacky Wednesday, dude. What you doing, man? What you doing? Crash on Wacky Wednesdays. So if you notice, the whole point of that was to show you we're not going to be computing this t. We're not going to be computing this standard error. We need to know conceptually what's going on, that the t controls how wide the confidence interval is. A t of about 2 is about a 95% confidence interval. T of 2 is not exactly a 95% confidence interval. Unless it's like 60 degrees of freedom. But the t controls how wide the confidence interval is. That's theory you need to know. The standard error also controls how wide the confidence interval is, but the standard error is just a measure of uncertainty in whatever you're estimating. And we're trying to do predictions right here, or confidence intervals for the mean of y given some x. So the standard error is your uncertainty, and the t is based on your level of confidence. That's a really good thing to know, that the t, I keep saying that, and Alex does a great job of putting test questions. He's got so many ready for the final. Like, I thank you, Alex. I'm going to be looking at those when I'm building the final. But the t, I feel like this is going to go up there. The t is directly connected to our level of confidence. The t is directly connected. The larger the t, the larger our confidence. It literally is that. And we let R figure that out. We're not going to do that by hand, especially in this class. So we have the difference between a prediction and a confidence interval, which we've been stating repeatedly, that a confidence interval is for the mean of y given some x, and that the prediction interval is for an individual. The difference between predicting the average tip on all tables that spend $20 and predicting the tip on a table that spends $20. Which of these is a table that spends $20? Which of these is a table that spends $20? The larger the p-value, kind of. Confidence intervals won't have p-values. And it would technically be the smaller the p-value. But they're kind of related to tasks. Good, Philip, right there, 100 points. Confidence intervals don't have p-values. The t we use is just chosen via the level of confidence. So I know you often get a p-value from a t, and tests and confidence intervals can be used interchangeably. But when you talk about a confidence interval, you literally pick the level of confidence. which would equate to generally smaller p-values on tests. So it's kind of the larger the t, the more it relates to a test with a smaller alpha. So if you want to hear that again, the larger the t, the more it relates to a test with a smaller alpha. Because a 95% confidence interval is the same as a two-tailed test. We'll come to the same conclusions as a two-tailed test with what alpha? It's like a stats 1 review. 95% confidence interval will come to the same conclusion as a two-tailed test with what alpha? 100 points first person. 95% confidence interval will come to the same conclusion as a two-tailed test with what alpha? 95? What's the answer here? So 95 on the inside. What's the two-tailed test? Boom, right there, Ben, 100 points. Yep, because Ben was just into one, yeah. So, because if you got 95, yes, Andrew, 100 points, and everyone out there getting 100 points. Why not? 200 points max. You guys are doing great. So, 95% confidence interval comes to the same conclusion as a two-tailed 0.05 alpha test. It's just the outside. 95 inside, 5% outside. So, it's mechanically the same, but you pick your level of confidence for these tests. Does that make sense? When you do, or for these intervals, when you do a 95% confidence interval, there's no real p-value in the background holding you to anything. You pick, I want a 95% confidence. I want a 98% confidence. I want a 90% confidence. So keep changing colors for some reason. If we were to predict for a table, we'd want a prediction interval. If we were to predict for a table, we'd want a prediction interval. Got to pull up the David M. Lane for those. Yeah, we don't need David M. Lane anymore now. We just let it do the work for us. We just say, it does it. Here's how you visualize the model again. We're seeing this. There you go. Here you can see the confidence interval for the mean. This is for all individuals that have an educational level of 4. This is for an individual. Do you notice how the prediction interval contains pretty much all the points? And that's what you want for the prediction interval. The confidence interval does not contain all the points. The confidence interval kind of does a meh. But I mean, it's for the mean. And what do you notice here? Over here at the end of this, it's not going through the middle of the data. Ooh, there might be a linearity problem. That's a linearity condition. Is it enough for us to say there's a problem? Yeah, probably not. So this right here is also 1 point. Is that enough for us to say that this is not going through the mean of y given some x? Yeah, probably not. It's 1 point. 1 point. So I don't know. It's not good that it doesn't go through it, but it's 1 point. You'd have to go directly through 1 point. Extrapolation, pretty easy topic to understand right here. What is extrapolation? And we have to do this a lot of times. Extrapolations are when we predict outside the bounds of the x for our model. So when you extrapolate, you're going beyond the model. And so when can you tell it's a linearity problem? Great question. Linearity is a problem when the red line right here, your prediction line, this is the prediction line, this is the y-hats, everything right here is your predictions, is not going through the middle of the data. So here, the red line is going through the middle of the data. Here, the red line is going through the middle of the data, which means the average residual is what? If the red line is going through the middle of the data, the average residual is what? Who's got it for 100 points? If the red line's going through the middle of the data, the average residual is what? 0. You got it. So, yep. So this is what the normal with a mean of 0 and a constant standard deviation shows us. So right here, we see that the red line is going through the middle of the data, but here, which it's only based on 1 point, the average residual looks to be about negative, it's like negative 800 or something. Whatever this distance right here is the average residual at that point, but there's only 1 point. So it's kind of we're basing it on very little data. Here, the average residual might be about here. Is everyone saying this is about the average residual because that one's a little bit lower? This is about the average residual here. And so the mean of the residuals is not 0 at this point. So, but it's only 3 points. So maybe, like if we had 1 point here, it would fix it. So it's based on very little data. So I'm not really ready to say that there's a problem with the linearity condition here. So you want the red line to be going through the middle of the data. That's like the goal of linearity, is that the line has a mean of 0, like the residuals are. Does that make sense? Hopefully that helps out with Ben. Does that make sense? I think hopefully that explains it. You want the line to be going through the middle of the data. That's the linearity. And so when we do extrapolation, people always wonder, why does Dr. Petrie not teach this class? Awesome, Megan, 100 points right there. So, and Ben asked a question too. So this is Dr. Petrie's weight loss. This is real data. And Dr. Petrie started out at about 162 pounds. I can't imagine. I think I saw him at that weight. I don't know. He'd laugh. But he started out at like 162 pounds. And in 35 days, he lost like 12 pounds. That's. I mean, when you weigh 160 and you would lose, I mean, if you're trying to lose weight, it's all up to you. It's whatever you want. And so he lost like 12 pounds. And so what would happen? This is like literally like 6-7 years ago now. So what would happen to Dr. Petrie following this trajectory? Where's Dr. Petrie going to go after like 6 years of this trajectory, or after just like another 4 or 5 months? He would vanish. He would vanish. He would cease to exist. A disaster. So Dr. Petrie would vanish away. But the truth is, with weight loss, what you're going to see with these weight loss models is people, go down. Didn't use crash. I know. I don't think he did either. You should watch Dr. Petrie code. He's so quick at coding. It's insane. Like people, like he just starts. He's like, I broke it. And so Dr. Petrie actually leveled off at a weight right here where he found a weight, and you're right, he would disappear. Great answers, 20 points, all his answers. He found a weight that he liked, and he stayed at that weight, and he was like, okay, I'm going to stay at this weight. And so you can't assume these models will continue. And that's the biggest thing. And like, once again, I don't try to be political in class, but when it comes to climate change models, I really think we have a good understanding of one, like, people always say like, well, in the 70s there was global, people thought there was global cooling. And the answer is, well, we didn't have as good of an understanding of the climate as we do now. And we have more advanced computers. Now, that's not saying we're right now, but I would say that we have a better understanding of what is going on and how humans impact it. So when you look at what we knew about the climate in the 70s, because there's things that impact the global warming. So we see things like methane, water vapor, and CO2. And the reason that we actually see the warming is because these molecules are opaque to the sunlight that comes in. And that's why they're called greenhouse gases, because being opaque means that we're going to see the sunlight come in, and then when it hits the earth, it's going to bounce back up, and then it's going to bounce back in. So it's going to let it in and then kind of trap it in, i.e. a greenhouse gas. It creates this greenhouse effect. But then there's a lot of variation in this. Where does methane come from? It comes from farming. It comes from, trying to think, CO2 also comes from volcanoes. So we have the anthropomorphic impact. We have the human impact. Is that the right word? Human. So we've got the human impact. We've got the natural impact. We've got different sources of human impact. It's a big complex equation. And so that's why I'm like, okay, we need a really, like, I don't think this should be anthropogenic. There we go. 100 points, Brad, right there. I was like, anthropomorphic is not the right word. Anthropogenic. So as anthro, I was like, the root of the word is right, but I'm missing the end of the word is wrong. And so with this right here, you can tell that it's a very complex thing. And I don't like it when people say, like, I want people to like investigate it. I want to be like, okay, let's get better and better data. And so the problem I have, though, even though I hold the position that it's something going on and the data suggests it, is that sometimes people will make climate models, and let's go see it. I'll pull up in the background. And we'll make climate models sometimes that predict out 100 years. So global warming prediction. I've seen a lot of models that will predict way out into the future. Yes. And good. Oh, I like this one right here, and I'll show you why. The further we predict into the future, the further we extrapolate what will happen to our uncertainty. The further we extrapolate into the future, what will happen to our uncertainty and our predictions. And this is a really great model that shows it. Like, I actually like what this model is doing right here. The further you go into the future, and this model is looks like they're using more uncertainty. That's literally it, because you're predicting further out, and every one of these models is pretty much showing it. You can see the wider bands. So, and it's just more uncertainty. The standard error gets larger, and that's what uncertainty is. So when you do these models and see that one's not moving out, and so I don't like this one. I do not like this model. And it doesn't look like the person was doing, I don't know who made this. Sorry, person who made this. But they don't have their uncertainty in it, because you need to show your confidence intervals. And I'm not saying these are wrong, and that's what I don't think people get sometimes, is I'm not saying these predictions right here on this yellow one is wrong. I'm saying we have a lot of uncertainty in the predictions. So it's not like, oh, these are wrong. It's like, we have more uncertainties. But volcanoes have been going off for millions of years, so wouldn't the CO2 outweigh the greenhouse gases humans have been? Yeah, I don't know. That's a good debate. You see that's the thing. Whenever I do the data on this, I always say like I'm not a climate scientist, so I don't know how to completely. I do understand the idea of what a greenhouse gas is. I do know the main greenhouse gases, and but then when it comes down to it, do I understand the science? Like I'm not a climate scientist. I'm a person who does data. So then I can't tell you, because the problem is stats doesn't show a cause and effect. Correlation is not causation. So we might say things are correlated or connected, but does that mean they're causally linked? It's very hard to say. And we really, it like to run experiments, the way that we do stuff, it would be nice if we could have an exact percentage of how much humans have. Yeah, Ben, I agree. And this is why I never want these things to be political, because to me, this is just about data. And then, like I feel like I'll never make any, Andrew, the golden rule of correlation, it's not causation. But then people are like, are you saying humans don't have an impact on it? No, I'm like, I mean, I due to the science, I think we have good reason to believe that our, like the way it actually acts, it's really all the cal farts. Yeah, methane. There's the issue with methane. And so this is the science part of it. Like what we're talking about right now is the science. Like you have to say, well, like how does the methane impact us? Like how does factory farming impact us? And then someone might say to people, well, the methane won't have this impact. And this is the kind of discussions I like. And then people get mad. Deforestation for more. Yep, there you go. So it's kind of like a cyclical cycle right there. We deforest more for more cows, and then the cows are putting off more methane, and then the CO2 can't be taken as much by the trees. And this is the kind of working model we believe in science that is explaining the human impact on climate. So that's the thing to debate, and that's the thing to come out with science. And so, and where the stats jump into it is where I see extrapolation. So we're jumping back to extrapolation right here. And feel free, you can say any opinion you want. Be like, it's wrong, it's right. Bring the science, bring the data. That's what we do. And I think people go like, they don't understand sometimes if I say to somebody, I don't like models that predict 100 years in the future. They're like, wait, are you saying it's not going to happen? And I'm like, no, the amount of uncertainty we have in 100 years is way greater. And I think this model does a great job of showing 3 different models with their overlapping intervals. And we've got like a really large increase to slight increase. Now you might say a slight increase is still bad. I'm not saying it's good or bad. I'm just saying there's tons of uncertainty here. And there's one of them, and I don't see it on the page, but one of them that shows multiple models. Look at that. And they're showing the observation. So that'd be interesting. We should look at what this one was talking about. We don't have observations in we're not to 2030 yet. Maybe I don't understand what that model's trying to say, because we don't have look at that. But it's not saying these are wrong, given how 2020 is going. 2020 has reset our minds on how things work. Dennis, 100 points. Yeah, so really you can see anything should be showing the uncertainty increasing. And there's so many models out there, lots going on. What do you look at where you get reliable data from? What is it? NOAA? I think NOAA is the site I go to get my climate data. National Oceanic and something, NOAA. I downloaded it last in like 2018. I used to mess around with the data more, but I think it's NOAA, and they have the ice core data going back further, and then they have the satellite data. NOAA, yep. So that's where I get my data from, and I analyze that data and run the time series analysis on that to see what the coefficients are in the model. So, but hopping back. Wacky Wednesday. He's around still. So this is my last little side on this. If Brian could have his perfect world, we would have not Bill Nye. I had dinner with Bill Nye. That's a long story. Not like me and him personally when I was on issues committee, but I had dinner with Bill Nye. He's interesting. He's a smart man. He's an engineer. He's a smart man. It was an interesting dinner. There we go. National Oceanic and Atmospheric Administration. There we go. And I will say this, Dr. Seaver and I have very differing opinions on climate and climate change models. And Dr. Seaver, so just so you know, like someone I work with, who one of the great mentors of me, those might be books for me see what these books are real quick. This is for Charlie's class. I should show Charlie these. I should have shown him. I was just in a meeting with him. They got water damage, though. Oh, look, they look horrible. Yeah, here's the book. It's green. If you can't tell, the other one's green, too. Well, these are Stat 365 from so long ago, and my, like, air conditioner dripped on them. So those are my... who's that? Oh, that's interesting, Alex. That's interesting. Anyways, no comment. It's yeah, interesting, her opinion, yeah. Yeah, anyways, after this 2020. So with the biggest thing right here that I'm pointing to, and if I can't stress one thing to, if I can't stress something to people more, it's, like bring data. There's, when you come to a discussion, especially, Dr. Seaver and I disagree on this topic, and I still respect him 100%. And he brings data to me, and he'll joke with me, and he'll be like, Brian, you're wrong or something. He'll just laugh, and we'll laugh about it. But then he'll bring data, and he'll be like, here's why I think this, and he'll always have a data-driven like way of doing it. So someone I respect has a very different opinion than I do, or different viewpoint on this, I should say. It's more than an opinion. It's a viewpoint based on data. And so that's the one thing I can not state enough to everybody is, try to get the data to back, don't try to get data to back your viewpoint, but try to have data that backs what you're saying, and be willing to look at data that people present, and then, make your model from there, because we do these things in our mind. If you can base your opinion on valid and reputable data, yeah, exactly, and that's the thing. And then if someone says, well, I have other data, then listen to their data. If someone says, well, I have data that suggests this, be like, okay, what's your data? And so Dr. Seaver shows me his data, and maybe it's just personal biases, which I can't control, that make me not, but I say like, okay, I understand, but I still don't weight what you value. Like, I don't have the weights on what you put certain things on. So sometimes you just come to different positions, and that's the way it goes. And then you still say, I still respect this individual, and they're still very intelligent. So if I can't say one thing to everyone in the class, it's like, once again, have respect for each other and be willing to listen to each other. That's Brian's advice with Brian, part of the day. That's what we say. So let's do this. I just see way too often people citing data with the sample size that, yeah, that's it. Yeah. And then what would be really large? First person, 1,000 points. What would be really large if someone has a very small sample size? What would be really large if someone has a very small sample size? What would be really large if someone has a very small sample size? This is huge. We're bringing it back to the topic of the day. What would be really large if someone has a very small sample size? Grant 1,000 points. Right there. That's the stats. You would tell them, you would say to them, and then their p-values are going to be high. If they have a lot of uncertainty due to small sample size, which literally it's in our equations today. Look right. I'm sorry, guys. I don't know how to drink. You just said it, that if someone has a small sample size, that's going to increase their uncertainty. That's stats. You'd be like, your sample sizes are too small. You got too much uncertainty. Yeah, no, right, Brad. So yeah, it's all about the stats. And it's someone's like, well, the numbers suggest this, and be like, well, you got a sample size of 4. And they'd be like, well, the numbers still say this. You'd be like, but there's too much uncertainty in that estimate to trust it. The confidence intervals are going to be too wide. Your p-values are not going to be significant because your sample size is too small. And they're like, well, it still says this. You'd be like, I'd prefer we get larger amounts of data, which you're not saying they're wrong then. You're not saying they're wrong. You're just saying you don't have good reason to believe it yet. So you're like, I need more data before I believe that hypothesis, before I reject my null and say there's evidence for your alternative. So that's how I work with data in my head. It's like, well, do you have enough evidence to support what you're saying? Do you have enough degree of evidence? I love stats. If you guys can't tell, I love some stats. Stats is awesome. So let's talk about making good models here. Like, what's the point of making a good model right here? Is it needs to follow the assumptions. And this is probably one of the easiest parts of the final. This is probably one of the easiest parts of the final. We need to visually check and do what's called the check regression. Here, I'm going to hop over here to the main screen. You write that red book. Man. One of these days I want to get that Red Bull sponsorship. Red Bull's like, yeah, everyone loves us because we're Red Bull. And I've had people say, like, I don't like the taste of Red Bull, and then they're like, but I need it. And I'm like, I like the taste of Red Bull. I would just sadly drink a Red Bull every day. I mean, I do already. That's bad. Okay, so here's the check regression. And since I know how to read this, boop, I can analyze this pretty quickly. So when I analyze this right here, there are 3 things to check. The 3 things to check are as follows. We have here the linearity, equal spread, and normality. Did everyone see this? Linearity, equal spread, and normality. Write this down in the chat. Step 1, look at all the p-values. Step 1, look at all the p-values. 20 points in the chat. Get those 200 points today. Step 1, look at all the p-values. Boom, Alex gets 100 right there, being first right there. Step 1, look at all the p-values. So we need to know the first thing we're going to do is we're going to look at the p-values. Now, when you look at the p-values, if the p-values are low, you reject the null. Now, the null for linearity is good. The null for equal spread is good. The null for normality of residuals is what? The normality of residuals is what? So the null for linearity is that linearity is good. The null for equal spread is that the equal spread is good. The null for normality of residuals is that, not a trick, it's not a trick. The null for normality is what? The null for normality is what? The normality of the residuals is what? Good. Casey, 100 points right there. Yep. And so think about this. The p-value here for the linearity is low, meaning we reject that linearity is good. So it's not linear. The p-value for equal spread is low, so we reject that the equal spread is good. The null for normality of residuals is low, or the p-value, excuse me, so we reject the null. So is this good or bad for all of these tests? The p-values are all low, and we're rejecting the null. And this is where people make a mistake on the test. They say, oh, this is great, low p-values. Yay, low p-values. Woo, reject the null. Wait a minute, the null was that they're good. The null was that everything's good. These low p-values are very, 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 very bad. This means that there's an issue with linearity. There's an issue with equal spread. There's an issue with normality. This is the key thing you need to know, that you want these p-values for these tests to be very what? What would you like the p-values for these tests to be? You'd like these p-values for the test to be what? Because you don't want to reject the null. 100 points first person. You want these p-values to be very what? High. Brad right there, 100 points. You want these p-values to be high because you want to let the null fly. You want to say, okay, linearity is great. Equal spread is great. Normality is great. You want the high p-values because you want to pass the test and be like, yeah, everything's good for the regression. If you reject the null, you're saying, ooh, there's a problem with this. This is where people get confused because usually people think low p-value good. Low p-value only means reject the null. That's all low p-value means. So maybe you want to reject the null. Maybe you want to not reject it. And if you want to use your regression, you want to not reject the null. So, and by not reject, I mean fail to reject or retain the null. There's lots of words we use in statistics. I like reject, not reject. It's my favorite way to phrase you reject the null or you do not reject the null because that's complements because you have to do one of the two. You have to reject or not reject. So that is the first thing right here. Let's hop back. So what are these tests? You can go away, Crash. You've already appeared a few times today. Is there a p-value you need to reach to not reject? Good question, Dennis, right there. Anything below 0.05 is reject the null. Below 0.05 is reject the null. 0.05 or above is not reject the null. So below 0.05 is reject the null. So when it's below 0.05, reject the null. P-value below 0.05, reject the null. And here's our key assumptions, 100 points, Dennis, right there. Key assumption right here is normality of residuals, linearity, and equal spread. Literally, we've covered this a few times. So is anything above, it would be not significant, and we want them to be not significant. So anything above 0.05 is not significant, and you do not want significant p-values here. If you want to use your regression, bigger is better. Yep. So the higher it is, the better it is to use your model. Be very careful because this does not apply to all p-values. It's only when you're doing the assumption test for the regression. So when you're seeing if we pass the assumptions, this is a keynote. Passing the assumptions in the regression is having p-values above 0.05. Passing the assumptions in a regression means having p-values above 0.05. So that's key right there. Anything about 0.5 is not sufficient, which is good for the assumption test. Boom, Philip, right there, 100 points. Yep, that's exactly right there. It's good for the assumptions. You want low p-values if you're seeing if something's significant in a model, but if you're looking at an assumption, the assumption is good. So you start out with the null that the assumption is good until you have evidence it's bad. Think about this. Would you start out assuming you can use your model, or do you say, no, I can't use my model? You start out assuming your model is good until you have evidence it's bad. So that's why the low p-value is evidence of a problem with your model. The high p-value is there's not evidence of a problem. So high p-value means we're good. There's no evidence of a problem. Low p-value is, oof, reject the null. There's evidence of non-linearity or non-normality or non-equal spread. So that's why we have kind of a flip in what happens here. And that often messes with people's minds. I've seen it. I've seen where they're like, it doesn't make sense. So here we write here, implications. If the regression model provides a reasonable reflection of reality, this will be, we want it to be the same equal spread right here. We've already seen that, so that's good. Pretty much, yeah. So that's exactly right here. The regression model is innocent of being a bad model till we have evidence it's a bad model. So it's right here. And we want our regression model to be a reasonable reflection of reality. So here we are, the residuals. Yep, just talking about it. So this right here is a good regression model or a bad regression model. This is a good or bad regression model. Look at this regression model. Ooh, look at that one, that singular point. That one point which shows up over here, that one point. 1 point, and maybe that's 1 point, like a little far away, a little far, but it's a little far. Is this a good or bad model? This model, nobody knows. I'd say it's great, and don't worry, it's an excellent regression model because we have a linearity going the middle through it. The residuals generally follow like a 68, 95, 99.7, because like 68 is contained within here. Like, do you see how like if you drew a normal model, this would be like the tails of it? There's points that are a little further out, but they only occur like 1% or less than 1% of the time. So 68, 95, 99.7. So you really don't see the outliers, but maybe 3 standard deviations out. And then we have equal spread. We see the homoscedasticity. So we see it's very good. Equal spread might be where it's an all-star. So we want our models to look like these. Like if you're thinking, what should a model look like? That is a regression model. I mean, it's not perfect, but it's really great. And so this is kind of our metric for what we should compare to. And this is a great residual plot. What is a residual plot? It just shows you how far away these points are from the line. Anything that is on the line or very close to would be on the line or very close to it. So anything right there has a residual of 0 because it's on the line. So we don't want to see anything crazy in the residual plot. We want the residual plot to look completely random. That's a key thing right there. I would love to put that as a multiple choice on the test. The residual plot should show which of these would look like a good residual plot. It should look completely random. And sometimes, yep, Brad. So in here, I'll show you, I'll have to hop back to the other screen. It gets more complex because there's multiple residual plots. Brad, 100 points, because that's why I say in 201, and that is one type of residual plot. So what you can do, because I've got a model in here, we don't do this, but there we go. Here's a residual plot right here. Here's a normal QQ. There's another standardized residual plot, and then there's the residual leverage plot. So you can just take your model and make it flat, and you'll make one type of residual plot. So you can literally just take your visualized model right here, and you can just make this model flat, which I think we saw. Do you see that point there? And then it kind of got the bend. So we should see, there's the point there, and there's the bend through the model. So this is if you look, we should have a 0 in here. Where's the 0 at? Yep, there's the 0. And notice here the bend at the top of it. Do you see the bend at the top of it right here where the model's above it? This is our linear model. And so take note of this line going through the center. There's the point above it. And then at the top, all of our points are below it. So this is literally, as Brad pointed out, our model right. Whoa, what are you doing? There we go. It's right here. You'll notice there's our point here, that top point we saw earlier. And there's our model, which was the flat line, and our points below it. Great job, Brad. Brad, that's worth 1,000 points. Remembering stuff from 201, because I literally say in 201, take your model and make it flat. So you take the model here and make it flat. or I mean, if it's lower, you make it flat, and that's one type of residual plot. There's other ways to plot it too, but this is a very acceptable way. And yeah, excellent memory right there. So there we go. So we have, and this is a different type of residual plot. If you notice, it's doing it versus predictive values. So they're doing it slightly different here. That's why I was like, there's different types of residual plots. Like, but you can just let it plot for you. These are all great residual plots. These are excellent A+ residual plots. This one is just there's not evidence of a problem because there's gaps, and you can't say there's a problem. You just be like, well, I don't know, but we can't say there's a problem until we have evidence. And these are perfect. Like if you see these, you've got A+ residual plots. Like those are A+. Now the bad ones. This is evidence of curvature, which we kind of just saw in ours. This is evidence of heteroscedasticity. This is evidence of outliers. So you've got outliers in your residual plot. The linearity is good. The homoscedasticity is good. This has non-homoscedasticity. It's heteroscedasticity, non-equal spread. This has non-linearity because the model bends through it. So does everyone see curvature as a problem, which is linearity? We have non-equal spread, which is also homo versus heteroscedasticity. And then we have outliers right here, which will probably hurt the normality of the residuals. So we don't want outliers because that'll hurt the normality of the residuals, because these are like, that's like a z-score of what? What do you think the z-score is here? Be careful. The answer is not where that hits. 1,000 points first person who gives me a z-score they think that is, that I think is close enough to it. I've got a range in my head. That I think that's a z-score of. Be careful, I'm trying to trick you with this by doing that. Who has a guess? 1,000 points per person. Crazy points. Because we're not done yet. We still have 14 minutes. What is that a z-score of? What do you think that z-score is? Now, a z-score is how many standard deviations something is above or below the mean. So, no one's got it yet. Well, but look, it has to be a what z-score? Something very, very important. It has to be a what z-score? It has to be this. And if it's -2, it would occur about 2.5% of the time. And this does not look like it would occur 2.5% of the time. So I'm going to have to toss this question. I thought it was a really tough one. No one said a number I think it could be yet. I might have to toss it. I'll give it 5 more seconds. The z-score has to be negative. It has to be negative because it's below the mean right here. It has to be negative. Brad right there, -5. I had in my head the range of -5 to -20 or so. This is super unusual. And remember, a z-score is how unusual something is. So when you say that this is -5, it's very much below the mean. So Brad, another 1,000. Gosh, Brad, yeah. So this is super unusually low. Like, it's not kind of unusually low. It's super unusually low. Like, if this one's +5, this would be like a guy who is 6'10". So it's like, this is an extreme outlier. Maybe it's 7'1". Like, that's an extreme outlier. So these are extreme outliers. They have extremely large z-scores or in terms of absolute value. And this one is extremely negative, and this one's extremely positive. So be very careful. Understand that we would kind of scale these things, and we'll see that more here in a moment. So the biggest thing right here, when you do these things, when you look at the p-values, is the first step is we're going to look at the p-values, which we'll do here in a moment. But then the second step is we're going to look at the plots. Once we look at the p-values, if we fail any tests, we will look at the associated plots. But there might be small problems. So once again, there can be small problems, but we don't want big problems. So we'll look at these plots here in a moment, and this is going to be a big part. So it's showing it. Here we go. I like these plots better. This one right here, let's look at what we got going on. The first one right here is testing the what of the model. The first one right here with this line going through is testing the what. This is a big thing. The first plot right here is testing the what. You should know this. The first plot right here is testing the what. The first plot is testing the what with the line going through. What were the 3 conditions? They were linearity. Oh, there we go, Brad. Yes, linearity. This is testing. And also Stevenson right there, 100 points, both of you. We got linearity. And then now, what's another condition we have to check? We had linearity, And it's also checking equal spread. East Stevenson, you're at the 200. Great job right there. We have equal spread here. Does this look like this has equal spread at all points? Does this look like decent? Oh, ooh, look at this. There's only 1 point here. Oh, I don't know if that's equal spread because there's 1 point and I can't really tell. No, that's not. It's 1 point. You don't know the spread at that point. Oh, wait, this is smaller. Well, there's only 3 or 4 points. But does it look generally like the spread is pretty equal across here? Does this look pretty equal to everybody? Like it looks kind of consistently spread? Does it look like the line goes through the middle of the data? How are we looking? Good on this one? Like it looks kind of equal spread. It looks like the line goes through the middle of it. Yeah, it looks great. Awesome. The last 2 plots. And if you remember, this could definitely be on your test. How do we check normality? With a histogram or with a normal quantile plot? How do we check normality? With the QQ normality plot or with a histogram? How do we check normality? With the histogram or the QQ normality plot? It's called QQ plot, normal quantile plot, normality, normal. It is with the QQ plot, the normal quantile plot. So you should know the name like normal quantile plot. Histograms are based on bins. They're not horrible for it, but they're not the best way. Normal quantile plots will always give you the points. And if you remember how this works, this was from when we tested means or medians. So when you want to use means or medians, you have to know if your data is normal or not normal. And we're not testing means or medians here. We're just seeing if the residuals are normally distributed, which is what we want them to be. We want them to follow a normal pattern where 68, 95, 99.7 is contained within the bounds. And if you look right here, this does a pretty good job. The red line is the amazing line that we want to follow. And then these are the like so-so lines. So overall, this does great. This is a great model. This is excellent. Looks great. Let's get another one here. So here we are with really bad linearity. So the linearity here on this one is good. Really? That's really generous to say that's good. I don't know if I'd say that's good. This one right here is really, really bad on the QQ plot for normality of residuals. What is the big problem on this plot? It does say normality is violated, but I also see another problem. Yeah. It's so funny to let the last one pass. Update this. Do you see it? Do you see it? Yep. And this right here, be careful. This is a trick I do. It is bent away here, and this means if it bends here, this would, and I think you guys are getting it, and this is the mistake people make, is this would be a violation of normality, and this is a violation of linearity. Be very careful. That's where I see mistakes, is that this looks like it fails the linear condition, but this is if it follows the normal pattern, the normal curve. So that's where people make a mistake because they say, this is a violation of linearity. No, that's a violation of the normality. This graphic right here, please take a note, is checking only normality. This graphic right here checks equal spread and linearity. Equal spread would be if there's an equal spread of these points, and it looks to be, but the linearity fails because the line does not go through the middle of the data. Does that make sense? The linearity fails because the line is not going through the middle, the mean of y given some x at all points. It's bending, the line's going below it, the line's going above it, below it, and then I guess through it, but hey, you tried line, but you didn't do it. So I see the violations here as a violation of linearity and a violation of normality. The linearity looks to be a bigger violation to me. Equations, fun, won't be on the test. Here's what outliers can do. What can outliers do? I think we already mentioned this. Outliers can do anything. They can make a slope positive, slope negative. They can do anything, which is kind of scary. Outliers can do anything to our regression. For QQ plots, are the tail opposite of the skew of a histogram? Kind of. For the QQ plot, if it's right skew, it'll bend this way, and if it's left skew, it'll bend this way. So it kind of pushes it in. Like, since this is right skew, it pushes it to the right. So the more right skewed it is, it'll bend like this. And if it's left skewed, it'll push out like this. So the skew kind of pushes it in that direction. That's how I put it in my head to remember. You don't have to know, like, I won't ask you, like, which way is this skewed from this, but it's got slight right skew because it's kind of pushed this way a little bit, and you can see it kind of bevy out this way. If it was more right skewed, it would push it in more this way. It'd push that center to the right there, and it creates this, like, shape like that when it's, like, more right skewed. You don't need to know that detail, though, but, I mean, I don't know. I've looked at a lot of them, so it kind of helps me when I look at them. I'm like, oh, there's a slight right skew with the outliers right here, and we can kind of see that right here. So good question, Brad, right there. And outliers can do anything. And so here we go. As our last part of the lecture, we'll be reviewing this more tomorrow. They'll always start the 0. They have 0 right here. So this is the observed, and this is the value. So they have at the middle of it right there, the 0 and the 0. And so it creates this plot versus what we observe and what we expect via the residuals right here. So don't leave yet, because we're almost done with the test. So once again, we want our p-values to be what? With assumptions, we want our p-values to be what? 20 points, say it in the chat. With the test, you want your p-values to be what? With the test, we want the p-values to be what? For assumptions. For the assumptions, we want the p-values to be what for the test? Yeah, good. Casey right there. Oh, gosh, I was scared. You guys, yes, that's huge. We have to know for the assumptions, we want them to be high. Great job. So an assumption is violated when a p-value is below 0.05. We want p-values to be more than 0.05. I can't say this enough. If you see me go through slides quickly, it's because I've said like 50 times. We want the p-values to be more than 0.05 because we want to use our model. We do not want to violate assumptions. We do not want to say we've messed this up. Now, I missed one step. Sorry, my brain jumped a moment. But if we have a small sample size, if our sample size is 25 or fewer points, game over. We'll write this down tomorrow. We're going to keep going. We're going to go to the very end of class. But if we have 25 points or fewer and we violate an assumption, game over. You stop. But if we have 25 or more points, if you have more than 25 points, 25 is arbitrary. I won't ever put 25 on the test. But if you have 25 or more than 25 points, then you get to look at the plots. So I'll do a few of these for you, and we'll review next class. We'll start next class right with this. So when we do this, let's go ahead and take a look, and let's see how this works. When you run the check regression model right here, you will be looking at the following. You will get first the p-values. Okay, I need your guys' help here. Are these p-values good or bad? Step 1, look at the p-values. Are these p-values good or bad? Are these p-values here, 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 good or bad? Uh-oh. Oh, no. Oh, no. Henry, 100 points, Henry. They're very good. These are great. I'm fine. All tests are passed because we don't reject the null. Everything's good. Linearity's good. Equal spread's good. Normality's good. Do you know what I can do now? I can use the model. That's it. I did the test. I looked. All p-values are good. I'm fine. Assumptions are passed. Good to go. Does it make sense, Alex, that we look at the p-values and if they're high, they're good? Does it make sense? The p-values here are high, which means we pass all the tests. This is good. We did not violate any assumptions. So step 1 is to look at the p-values, and I'm done. I passed step 1. You passed on step 1. You don't have to retry again. And you could look at the plots. Does everyone see that this looks pretty linear? The equal spread looks decent, and the normality of residuals looks pretty good. And only for the assumptions, Megan. This is for only assumptions. You have to make sure you know when testing assumptions, you want to pass. So let's look at another one. How do we do on this one? How did we do on this one? We've still got 2 minutes. We're going to do one more after this. How do we do on this one? On this right here, we do what? Step 1, look at the p-values. And how do we do? We did horribly. So now we look at the sample size for step 2. And this is not a pass or fail. If the sample size is greater than or equal to 25, we can continue. The sample size is greater than or equal to. So now, since the sample size is large, I can go back to step 3 and look at the plots. How does that equal spread look? How does that equal spread look? 1,000-point question. What is the only condition that's probably passed right here? 1,000-point question, last person, this is the last question of the day. What is the only condition that's probably passed? Like if you were to say visually, it doesn't look the worst. And it's not equal spread. What is the only condition that's maybe passed? The only condition that's maybe passed. Linearity, Grant. Nice job. Grant's right, linearity. Because the line looks to go through the middle of the data. That line right there looks to go through the middle decently. And the normality has a huge problem over here. The normality is, there's major problems there. There's problems-ish here, but the major problems with the high outliers up here, so that the QQ plot shows major problems with the normality. So great job right there. And that is the end of class. Is it making a little bit sense? So I would toss this. I would toss this model. I mean, it's the last thing I can say on this. I'd be like, yeah, this model is not appropriate. This model is garbage. We're gonna be like, toss this model out. Do people think they kind of understand what's going on right here with this? Like they understand the steps are, you look at the p-values, you say, okay, the only problem here is the normality of the residuals. So I'm gonna look right here. My only problem here is the normality of the residuals. And then I'm gonna go back to here. I'm gonna look at the normality, and it looks mainly to be due to these outliers here. So, I mean, you've got this extreme point. This extreme point is this point here. It's this point here, and it's this point here. And it's mainly due to that. And that's where the violation is coming from. Who feels like they kind of get this? Does it make sense that I'm going to look to see where the violations are? And it's with the normality. And I'm going to look back to the plots as long as we have a sample size of 25, which is step 2. And we do. So, yeah, it's 3 steps. Look at the p-values to see if there's a violation. Check your sample size to see if you can look at the plots. And then look to the plots to see if you can continue. Yeah, we'll practice it more tomorrow. I wanted to get us to here to where we could practice this and look at the, and I want to say this about this assignment especially. With this assignment, you want to kind of walk someone through what's going on. You want to show, here's where the violations are, here's what I'm assuming, here's where I see the errors. But good job. We did excellent work today. We have so very little to cover in this chapter. It's a very short one. We just have transformations, which that's just totally making transform models and outliers, and that's it. We'll be done about 30, 40 minutes into class tomorrow, and we'll get into multiple regression. And so we should be finished with multiple regression part 1 by the end of the week, which was my goal, which is awesome. This week was all simple and the start of multiple regression. But good stuff. Excellent work. Any questions about anything going on? There's always got to be a little bit more Red Bull. I liked when Brad said, I saw the Red Bull kick in. I should go watch that. The Red Bull. My hair is just it's so funny because I've been teaching online via my place for 3 months now. And I got a haircut a month or 2 before quarantine. And my hair's just getting so long. I can't decide. Never cut the hair again. Should I do that? I had the beard for a while. I don't know if people saw that. You were mid-drinking, got excited for someone giving a correct answer. Yeah, I love it. I love when people key in on answers and they're like, oh, this or that, or they make a comment and I still haven't gotten a haircut. Oh, Andrew, that's awesome. I wonder, everyone's got the crazy long hair. I'm gonna let my fiance cut my hair. So that's what I'm gonna do. Just be like, cut, do whatever you want, haircut. It'll be fun. We'll take a break in a moment. Also had an epiphany about the question last night. Oh, awesome. You decided to wait for a year? Wait, are you not cutting, what are you doing? I decided to wait for a year? Decided on what to wait for a year, Brad? You decided to wait for a year. I need to get Discord piped into here so that way, it'd be so crazy. I wonder, because I could put it so I could hear Discord. I'm going to check out my sister's new salon today. Oh, that's awesome. Well, maybe, I don't know. Maybe, yeah, that's the tough part right there. If your sister's got a salon, then it's that's awesome. Congrats to your sister, for having the salon. And it's a crazy time with, the world with 2020. 2020, you got to stop it. You gave us Tiger King, but you give us a lot of other craziness. COVID. Go away, COVID. We gotta beat COVID. This YouTube video has now been demonetized. Let's get a tiger for Stats Nation. That'd be awesome. We need a Codamundi. I knew an awesome Codamundi. Codamundis. We need more animals. That could be what we do with all that money. I think I can look at in the background right now how much money we made yesterday. I think I can say that on YouTube. I think I'm allowed to say those types of things. It's make a little money. It's weird because some days, we're doing good. We're making 20, 30 cents a day. That's good. it went up, which is weird. And what video? I can see what videos are being watched. So it's interesting because I can. Where can I go? Revenue. There we go. Top earning videos. Let me change the time period. There's so much cool analytics you can do with this. And what videos are people watching right now? So I can see what videos are being watched and where. Okay, see more. Here it is. So yesterday there was a spike in the 2-sample Z interval TI calculator video, and that was the one that made us pretty much all the money. The other ones are making us literal tenths of pennies. But I have no idea why the videos will just spike and make like 14 cents. Because if every video was making that have monetized, like made like 14 cents, then it'd be insanity. But like we saw a spike here on the 2-sample Z test, all of a sudden jumped to 32 cents on one day. So I have no idea why we see spikes on this. But one thing we were talking about yesterday, extrapolate the data 10 years out. Well, that's the thing. You're right, because extrapolation, to bring it back to statistics, extrapolation is going to be a very bad idea on this, because especially what we see right now will not be the same as during the semester. And we were talking yesterday in the Discord that if I'm putting out videos for 201, which I plan to, and go over topics with them and have like, hey, here's how to do the mean, here's how to do this, then those videos are going to be sent out to like 1,400 students. And if 700-800 of them watch the video, then we could see, with a bunch of videos, all of a sudden they could start not trending. We're not going to trend on YouTube. That'd be craziness. But the videos will start hitting the algorithm, and the algorithm will start maybe suggesting these videos to people doing statistics. Like if all of a sudden our students are clicking on our videos or Googling our videos, then the algorithm might say, oh, these are the videos people want to watch when it comes to statistics. And we do have a large base of students to pull from. So we could start becoming a suggested video to people when people try to be like, how do I analyze the mean, or how do I interpret standard deviation, or what is standard deviation? So I'm going to try to find the videos that are kind of doing well, kind of look at their pattern, and then try to model our videos doing those topics after them to kind of be like, we can make a video. Yeah. Oh yeah, I hope we don't see linear increase. I hope we see exponential increase. And so I want us to kind of, I don't know, because then we can, be the source of information when it comes to stats, and we can use that, if we are the ones getting the revenue from that, then that can go to our students, which would be awesome. Because then it's not my goal that like all of our students watch the monetized videos. It's my goal that we get other people from other universities to watch the monetized videos, that we can be like Stat 201 at UT and be like putting out the videos explaining the topics. So I'll do like short videos, I'll do longer videos, and that's what I'll be doing during July, is like trying to make more of these videos. And if all of a sudden next semester the channel's making like, let's just say ridiculous, like $5,000 a month, which would be ridiculous, would be absolutely ridiculous. But if that were to happen, things happen, we would just put all that money to scholarships or to tutoring. We're just going to put it right to the students. And it'd be a cool thing to deal with, to be like, okay, now like we do like 5 scholarships, $5,000 scholarships or something like that. I don't know. It'd be really cool. It'd be a cool situation to be in. I know. So stay tuned, and we'd do it for like HASM, or like we do it for business analytics students or HASM students, but we're just going to put whatever we get back out to the students, and that's the goal. But I'm going to head off here for a moment. I'll be back. Hang out if you want. 474. I'll see you soon. So bye for now, everybody. Bye. Hey everybody, it's Wacky Wednesdays, and I'm stuck in a cave, and the green screen's got green around me. It is time for Wacky Wednesdays. There's our man right there. There's our dude. I think everyone can still hear me. Yeah. Let's see. Sound a little quiet. How are we doing today, everybody? Doing some randomness to start the day. Good morning right there. Tag some people in the chat. Why the green screen's acting a little bit weird. Had green all around me. Got a green screen. Better. How's everyone doing? Can everyone hear and see me? I think I can hear and see myself. We're doing well. Awesome. It was so funny yesterday for 320. Everything went haywire. I was looking. Can you see? Oh, look. Why it's yellow. Why is yellow? Can anyone see whose name? Wait, there it is. Can anyone see whose name this is? Probably you can't see that from this distance. Ah! I'll show you the other. No one was able to read that, I think. Stat 365. Here, can you see whose name's on this one? You can see the black writing a little bit. It's Charlie Quick. I've literally got the books from Charlie from a decade and a half ago. What's up, Sarah? Good to see everybody. But I was going through all my stuff. I should show Charlie those books. But those are my old books from Stat 365 from Charlie Quick. Still hanging on to them, still doing stats, doing process control. But we today are going to do some fundamental of predictive modeling. Now, there's something good. So let me start with this. Some people have taken the test. Grades are looking great on the test. Maybe they can't look too good, but the grades are looking good. So hopefully the test is fair. Maybe it's a little too easy. But here's the thing. Maybe 320's take-home was a little easier, and maybe they'll find their test a little bit harder. Maybe you guys' take-home's a little bit harder, and you'll find the test a little bit easier. So maybe I found some good balance between your guys' take-home being harder, your test being easier. But I think I've only seen 2 grades on the test so far. You can't hear me? Can people hear me? Yes or no? Okay, good. Okay. No, it must be volume thing. Check volume. So, check volume. Say spell volume. Check volume. Check speakers. Check speakers. Check speakers. So, okay, good. Whew, scared. Because yesterday we had the issues. So, with this right here, we have the test. Make sure to take the test by tomorrow at 2 p.m. If the test doesn't go well, maybe there'll be a curve. I don't know. But right now, the average on the test, I think the average on the test right now is like a 98 because there's only 2 people who've taken it. But of course, the people who take it earlier are probably going to be like more confident in what they know. And so, the first 2 people to take the test are probably like, I got this. I know this. I'm going to take it. Boom, got it. And we did correct 1 error on the test. Hopefully it changed. I'll take a look to see if the error persisted, but I had 1 error on a question, which I corrected. And thank you for the person who caught the error. Really appreciate that. I was switching around multiple choice answers and I didn't change. I made 2 right answers. So if you get to a question that has 2 answers, I'll try to fix it. You do get your grade back right away, I believe, but you can't see what you got wrong. So you can't see what you got wrong, and I'll be seeing if that error I made on it carried over. I already fixed it for the 2 people who took it, and so there was 2 right answers. So if you do see something like that, I hope it changed it in the question bank. I changed it in the question bank, but I hope it changed it on the test. I'm too afraid to go in and change the test. But if you do see a question with 2 right answers, then I'll fix it. So I might have to go in and manually change everyone's, but I'll be looking to see what it does. But I'm hoping it kind of fixes it because I fixed it in the question bank. We'll see what that does though. That's got it. So with that right there, we are good to go. Any questions about the take home or the in class or anything going on? People got some awesome points going on. Keep getting those points. What questions does anyone have? Be working on the take home. Oh yeah, we're going to show this again. So when it comes to the take home, let's hop to the main screen. Let's jump to the take home. What you need to do is you need to go to this button right here. Make sure you're doing this. Can our cheat sheet be typed on Canvas? It's handwritten. It can be typed. It can be handwritten. You just can't write down stuff during the exam. Don't write down things during the exam. Do not have a pen out. That'll be big violation. Do not have pen out. Do not be talking during the exam. It does say when you start the exam, for those who have taken the exam, does it give you that screen at the start that says like, don't do this, do not do this, do not do this, do not have a calculator, do not have a pen out, do not talk to yourself. It should have those things that I put like, do not do this, do not do this, do not do this. And then you scroll down and it says like, by taking this exam, I am agreeing to these. And if I violate these, I might have to do so, yep. And so it should have that page with instructions that I wrote out there saying, do not do this, do not do this, do not do this, do not do this. So yeah, just follow that. Don't do the things it says do not do. And you can have your cheat sheet out. So, but just don't be writing on the cheat sheet, because then you could like write down like this problem was this. You could just write down the whole exam while you're taking it. So to load up your practice exam, let me save the 320. We're in the 320 folder. Today is the 17th. Oh my gosh. What happened to the month of June? What happened, June? Where'd you go? Where'd you go, June? So I believe I have the file. We can do this by going here. And this is the big thing. You need to go to downloads, and you need to go to the... Do I not have it on here? Wait. No. I might have to go download it. BAS 474 summer midterm. So you have to go here and open it. And if you notice, it's going to load in the function. So if you're having a problem, please email me with whatever you get here. Here I'm going to clear. It says to clear your global environment. It says to do all these. And so what I would suggest is following the steps right here where you clear everything. Go to here. So this is the steps on how to do this again. Go right here. Go to where you've downloaded the file. So I'm going here to downloads. I'm going to the file, which was the BAS 474 programming midterm. That's the practice. Where is that? Where are you at, file? I just saw you. I just clicked on it a moment ago. Really? BS 474. There it is right here. So you need to click on... I've lost my mind. There it is right here. So here's the BAS 474 midterm right here. I'm going to click on it, and it should start. There we go. I was worried. Warning, do try catch. That's a graphical error. So it has loaded everything in right here. So wherever you get to, these are just graphical errors because of the window size. And then we're going to go here to make my exam. Once you do this, put in your number, put in your actual ID. It doesn't matter if you put the zeros, it'll say like deleting the zeros. And then we've made the exam. Once you've done this, you want to go to exam, and this is the exam that was just made for you. So does everyone, these are the steps right here. Please tell me where you get to. If all of a sudden, so be working on this, be looking into this, make sure it's working, make sure you have your midterm created, it now exists, and you have your midterm. This is not your midterm. Make sure your midterm has your number. Do not, if you run this file again, you will overwrite it. So it's highly suggested you change this and you go to save as and change it to a new file name, such as like midterm. Don't change this up here either, because if you start changing this, like this is the, I don't even want to do it, because if someone does it, this is the absolute worst thing you could do, is start changing that. Let's say if you entered in, it's the night your midterm's due, it's Friday night, and you realize that your digit that you entered in here was one digit off. Like your ID is actually 251. I don't even want to type it in there. Should you change that to 251? Should you change that to 251? The answer is, should you change that? 100 points first person, 200 points max day. No, Andrew right there. Don't change that. And if you make a mistake like that, just please tell me. Be like, Brian, I misentered my ID number. It's this. Don't change that, because if you change that, it changes what random exam you generate. And if you change what random exam you generate, it changes what your answers will be. And if you change what your answers would be, your answers are probably going to be wrong. So don't change this. Whatever you do, do not. Like, literally, if you put something in wrong, tell me, Brian, I entered in the wrong ID. Now, if your ID is like your friend's ID, that's not going to look good. So if you're like, I entered in the wrong ID, for some reason I entered in my friend's ID. Oops. I'm like, what? Why did you do that? Don't do that. Why? That's bad. That's reporting you as student conduct. Because I don't know why you would be like, I didn't know that my friend's ID wasn't my ID. That was your friend's on your... Wrong button. That's why I'm shaking my head. So, Wacky Wednesdays. What's up? We missed you, Crash Bandicoot. So, The biggest thing is start. How are people doing? Remember, if I ask questions about this, you can answer them. How are people doing on the take home? How are people doing on the take home? Like pretty far, haven't started it. You can say like completed it, pretty far, haven't started it. What do you think? Doing good, like it. And so we got thumbs up. One person says good, around halfway, good, like halfway, good. What percent of the take home is pretty easy? What percent of the take home is pretty easy? What percent of the take home is pretty easy? You can answer that. We're not going like specifics on questions, obviously, but what percent of the take home is pretty easy? About 40%, 50%. Yeah, some of it's like kind of just basic. Like you just look at the question, you're like, okay, got it. That's good. A third to a half is, yeah, that's what I want to see. Maybe what percent of the take home is like, oh my gosh, I have no idea how to do this. Like, what percent of the take home is like, this is gonna be a question I get wrong. What percent of the take home is like, I guess that one's one that I'm not gonna get. Haha, whoops. Don't know what they want there. I asked 2 percentage questions. I think 1% I like this. Andrew 70% on that. So depending, which maybe I'll do a survey on this and ask people and get the distribution from the students. But we'll look at how the grades are and be looking through the notes, be looking through the assignments, be looking through too much. Oh no. So once again, we'll look to see how the grades are on the take home. If it's below a 75, I'll curve it. Once again, remember, if you do see grades on Canvas where it says the average is like a 68, that's because of zeros. I guess I wonder if I could supply to you the actual grades, but I think everyone trusts me enough to know that if someone's like, Brian, Canvas says the average is a 71 and you said you would curve it, I'd be like, that's because 2 people didn't turn in anything and they got a 0. So we'll toss out the zeros and we'll do the average on for what people turn in, because zeros dramatically impact averages, but then it's just a person who just didn't do the work. So they didn't put an attempt in. So we'll remove them out. Keep your spirits high. Yeah. Once again, remember, and I don't mean this in a bad way, it's kind of like we're being judged as a class. So if you're on track with the class, then you'll do all right. And the test looks to be a little bit easier. So if you get a good test grade, you can take a sigh of relief and be like, I expect it to be a 75. I'm kind of thinking it'll be a 75. Just from what I'm seeing, there's some parts people are finding easier and some parts people are finding tougher. I think it'll be about a 75. And so don't be like, I think if there's a curve, it'll be very little. I could be shocked and the average could be like an 80, 85, 90, but I'm thinking right around 75. Like I might do a 3-point curve. I think the biggest curve it'll get is probably 10. I'm not going to say I'm not going to, if something ridiculous happened and the average was like a 25, I'd be like, what happened? What happened? You can. I'm pretty vague on them. I kind of just restate the question, but you can ask. Always, remember, you're supposed to ask me. Don't ask other people. Like number 10, what the heck's going on there? Ask me, because even if you're like, can you just restate it to me? Curve so we all get 100s. No, but then how do we? I will say this. One of the most important things to us is the ability, and I'll show you something here real quick. Please. In 320, just earlier right here, in 320, I wrote this function right here. So this function right here, let's load it up. And I do have things outside the function. Plot, cool, I don't care. It's going to work fine. This function right here is used to predict someone's height. And it just says, what is your weight? So I weigh 188. It predicts me right here to be 70 inches. We could even have it print to the screen. Like you could go right here and you could say cat, and you could say, ooh, we can do, let's do it this way. We'll go cat, paste, the model predicts that you are, and then we need to go to total, and this is 1, 1. So comma total, whoops. What did I do? Oh, that's what I did. Really? What am I click? Wow, stop being weird. That's weird. What is going on? Don't. Come on, computer. 1, 1, comma, inches tall. And so we got this right here. You know what we could do? Oh my gosh. I bet. Let me run this right here and I'll show you another thing, which is a decent review. Because it's almost like this is a function right here. And I think that'll put the spaces right there. Let's run this. And you put in this, and you say, I am 180. The model predicts that you are... So this has to be rounded, because that looks ridiculous. This has to be rounded. We could do one test as a class. No. Not happening. So the model... Whoops. The model predicts... Here, 180. The model predicts you are blank inches tall. And now we're going to go over here to the end of this. And we're going to put a \n. And one thing you might not know, here's the thing people might not have known, is you can run a function by clicking on the last bracket, and it'll reevaluate the function. So I didn't have to go up there to the top. I just ran it on the last one. And now we get the model predicts you are 69.53 inches tall. Do people usually report their heights by doing this right here? Do people usually report their heights by doing this right here? And I wonder... Because we can turn this into feet and inches pretty quickly. Do people usually say I'm 69.53 inches tall? They usually don't say inches. They usually say like 5'9", right? So watch this. We could go right here, and why not take the value it predicted from total, and we're going to write it out right here. And we're going to take total, which is what it predicted right there. Total not found. Oh, because we're not storing it to the global. Well, it's this value right here. We're just going to store it here for the moment. Total. Cool. And yeah, it's not a matrix, but we're just going to manipulate the following way. Okay. So let's go percent 12. What did I just find? What did I just find here? This is how many inches somebody is, like after their feet tall they are. Let's go to round. Go to 0. Because usually people just say like 9.5 would round up because, you know, we're going to round right here. What's left? So that's what's left right here. And then we need to go to, we're going to go to total. And we're going to divide it by 12. And we're also going to take this and once again run it just to see what it is. You should always run everything to look at what it is. And we're going to round this to, and yeah, that'd be fine. Cool. Whoops, not 2. We're going to round it to 0. And oof. You know what we need to do? We need to go to floor. Floor does not take 2 arguments. Wait. Floor just takes 1? Oh, there we go. So we're going to do the floor of it, which is going to bring it to the lowest amount. So you might not have known the function floor. Floor brings it down. So 5.9999999 would be 5. So floor is going to bring it down. We would kind of need an if in here, like if somebody is like, if it says like I'm 5 foot 12 inches tall. So you could floor this one also, and then that would deal with the issue. Like we just would round down no matter what. So you wouldn't get something weird like I'm 5 foot 12 inches tall. You're like, are you 6 feet? We're like, well, not quite. I'm 5 foot 11.8. So you know what? Here, let's do that. Now it's going to make more sense when someone says they're 5 foot 11.8 or something like that. So if you look at this right here, this is the feet. And you know what we could do? Let's go right here and do the following. And let's call this feet. And let's go here and call this inches. That's just going to be easier to deal with. And so that's the feet and the inches. And we want the position right here of this, because this is now a matrix. If you're wondering why I'm doing that, it's because it's not a singular value. It's position 1, 1 in the matrix. So it's in the matrix. Predicts that you are blank feet tall and blank inches. So we need to put a end of the parentheses and then and blank inches. So blank feet tall and blank inches. 6 foot. The model predicts you're 6 feet tall and yeah, sure. Can you like the homework? Yeah, did I not do that? Let me do that right here after this. You got it. I will do that. I'm going to put a tall right here because is that going to have too many spaces? Sure, let's just do what happens. You know what I'm going to do? paste 0. Paste 0 is a special thing that does not put any spaces, and then it's going to do it like that. Okay, I think that'll do it. We're going to change this to feet. Did I not change that? Okay, that is where we want it. Cool, let's see if this works. Predict height, 180. The model predicts that you are 5 feet tall and 9.5, which is 5 feet, and there we go. That's going to be better grammar. So let's take a look. Let's run this one last time here. So let's run this one last time. Go here, and go here, and let's see this model for someone who's 210. The model predicts that you're 5 feet, 11.7 inches tall. There we go. So let me see, Caroline. Let me look at that in the background here real quick. Homework 4 solutions. I thought I unlocked those. Oh, I think I know I did it for 320. I'll do that. Caroline, send me an email. Caroline, 200 points for today. Send me an email, Caroline, reminding me to do that. I'll do it after class because that involves a little more switching around. But I'll put those up so people can take a look at those. So thank you very much, Caroline. Now, I want everyone to look at this because this is kind of what we need to understand with things like functions. One, when we build functions, we always want to return, and we're always trying to build better and better and better and better and better and better functions. So when you look at this right here, you could have that we don't even return. If somebody doesn't really know statistics, we might not even want to return that matrix to them. We might just return a prediction. The model predicts that you are 6 feet, 2.7 inches tall. So our goal with business analytics is the utilization of all of this right here. Don't do that, Andrew. So this is what we want to do, and we want to figure out ways to do the mathematics and understanding how to do things like this right here, like taking the position of something in the total matrix, the 1-1 position, because we saw where it was located at. It's located right here. That's in position 1-1. Dividing it by 12 and then doing something like floor. It's like, well, when do we need to know floor? Well, we don't want to round it because if you're 5.6, then that'll round up to 6. We want just the 5 part of it. So you could also do, not round, but you could report a certain amount of decimals. There's a lot of ways. There's always 10 ways to the right answer. But I think floor is the best answer. And then we just have to, it's going to look weird if somebody's like 5.11 point, I don't know. But there could be weird things. We'll just ignore the weird things for now. They're like very uncommon cases when it makes predictions. So this right here is an example of us building functions, but let's hop to some predictive analytics right here. Big stuff. Wacky Wednesdays. Say it with me, guys. Wacky Wednesdays. We got this. I've just got the button pressed. Okay. So with this right here, we are doing predictive analytics now. And this is where the real meat of this course starts to spin up. We should have now a good base of knowledge of statistics and how to use it. So the first few slides are going to be a little bit of review right here, but we have some key terms. In predictive modeling, we've got evaluation metrics. So you should instantaneously know, and this is where the final might be a little bit more difficult and where your notes are really going to help, what evaluation metrics we have per model. The generalization error, if this was a written test, I'd ask you to write down what a generalization error is, and you'd have to get it right. The generalization error is how well our model does on new data that the model has not seen, how well it generalizes to new data, which is the whole goal of predictive modeling. I can't make this more clear than to like highlight the words right here and to show you that in predictive modeling, the whole goal is to have models that work on new data. That's the whole goal of it. What is the goal of predictive modeling? Who knows? What's up, Joe? Good to see you here, Joe. What is the goal of predictive modeling? What is the goal of predictive modeling? What is the goal of it? Who knows for 100 points? Who knows? What's the goal of predictive modeling? Anybody know? Single person in the class? Kind of to predict, but have to models, predicting on new data, Jenning right there, you're right. Works on new data, it generalizes to new data. The goal of predictive modeling is to predict on new data, models that work on new data. That's so key right there. So we want to predict on new data. So wouldn't you need some way to evaluate if it works on new data? So we need some way to evaluate if it works on new data. And then we need some way to estimate if it works on new data. This part right here is how we estimate if it works on new data. And then we need some way to select our model. And this is a huge topic for the remainder of the semester, is the bias variance trade-off. And we'll talk more about what bias variance trade-off means and how if you increase your bias, you decrease your variance. If you decrease your bias, you increase your variance. So this trade-off is going to be huge because you can't fix both of them. You can have a very low bias model with high variance or a very high bias model with low variance. Or you could try to find this point where they even out, where you kind of get this happy sweet spot of bias variance. These are the review slides I was speaking of. We've already done classification, which we're doing in mostly descriptive. If you look right here, the classification we mainly focused on was describing our customer base. Now we could do that with prescriptive and predictive. Prescriptive should be in here also because we can make plans of action. But the first goal of clustering is to do descriptive modeling to say, like, here's our blank customers, here's our blank customers, here's our blank customers. And once you kind of describe the clusters, you would then figure out strategies. So I feel like there should be prescriptive modeling in there also. So you've got descriptive, predictive, and prescriptive, which we've covered in clustering. Hint, hint, hint for the test. So you've got descriptive, predictive, and prescriptive. Hint, hint, hint. I can't do that enough. But we've already covered this topic, so ergo could be on the test. So regression is what we are covering today. We've already looked at association rules, and there we go, clustering, so classification, but we use clustering as a type of classification. And so we mainly use that for descriptive, but we can come up with prescriptions also. But the main goal is to describe what is going on. And once again, let's start doing some regression modeling right here. Here's key terms. We got to pause on this slide. Generalization error is once again how well the model does in the long run on data it has not seen. So when you look at this right here, I love talking about Julio because he does so much cool stuff with the Yankees. He might want to predict how well players will do in the majors. So he would take data from people they already have. We're in the Cardinal shirt today. So Julio's going to take, oh, that's awesome. Joe, I'll throw some points your way, Joe, here in a moment. So stay around, Joe. If you stay a little bit longer, Joe, we're for review. I'll throw you some bonus points here. So when Julio wants to make predictions of how people will do in the majors, he would use the data he already has. And what is the goal for Julio right here? To predict how people are currently doing, or predict what? For data, he has what? And does he want to predict for one player in the future? Here we go. How players will do. He wants to predict for how players will do, like players that the model hasn't seen. So Julio's going to be like, okay, I've been in the majors. Like, he's been around since, like, I think like 2008 or so. He had a good 10-year career and stuff. Awesome career with the Rangers and all that great stuff. And he's like, I've got all this data on these players. I know how they are doing. Now I want to predict on players that are not currently, that we haven't seen yet. Players that are coming up into the majors. How will they do? We don't know how they will do. So he's making a predictive model. Like, he can describe what's going on. He can describe, which is a descriptive model, like players who do this and this generally do well in the majors. But then he's going to say, I want to predict who will do well in the majors. So he's going to have a generalization error of how his model does at predicting new individuals that it hasn't seen. Now, what do you think? Will his model work better on the data it's created from, or will it work better on the data it hasn't seen? Will the model work better on the data it's created from, the literal data that creates the mathematical coefficients for the model, or the data it has not seen, which the model's like, wow, I've never seen that data. Let's try to predict it. Which of those will it work better on? The data it's created from. And that brings us to our next term right here, which is the training data. The training data would be the people, the players that Julio already has data on. So the training data for Julio would be players he already has data on. I can't state it more simple than that. Like, players we've already seen if they're successful or not successful in the majors. And the biggest thing about this problem is you want it to be kind of consistent over time. Like, there can't be this shift in what happens in the majors. Like, maybe nowadays the majors changes who they recruit, which there's going to be changes over time. So you don't want to use data from maybe the 1970s. Imagine if Babe Ruth was transported to the future and Babe Ruth is like, I don't know how to do it, like an old-timey voice right here. He's like, I tell you what, you need one of those batters that holds the bat back here and swings, and then he's got the pants pulled up, and then, pull your pants up before you run. And I'm just running. Those old-timey baseball uniforms that look so ridiculous, and now our baseball players kind of look like action heroes almost. Like, they've got these like these, I don't know. Everything they have now is like. I just see the old-timey baseball players. I just laugh at them. They look so... I'm sure back then they thought they looked cool. I'm sorry. Cool is so subjective. I'm like, what could Babe Ruth possibly give as advice? And all of his advice is probably going to be not relative to today. So what am I getting at? If you were to use the model that Babe Ruth has, his model is going to be way off, and it's going to be ridiculous. Like, I mean, the baseball uniforms we have today are like crafted to optimize what players do. And Babe Ruth's idea is going to be like, no, Babe Ruth, you're not data-driven decisions. You're not, or maybe he's right. He's probably wrong, for at least today. He might have been right for his time, like on what worked in baseball, but the model has changed. So we have to look at the current data to make the decisions. And with this right here, has anyone ever seen those old-timey baseball uniforms? We got to see a picture of this now. We got to see it. Babe Ruth at bat. I'm seeing is there a good picture of this? I don't look so bad. He just doesn't look like a modern baseball player. Like he looks like, no offense, Babe Ruth, but you just look like, oops, we lost it. He just doesn't look like, go to main screen right here. I know Babe Ruth's like all-time great, but doesn't that look like maybe your dad like came out to like play some baseball? I mean, he was amazing. I mean, maybe that's more of him. Yeah, he looks younger there. But he kind of looks like, okay, he looks more determined there. Yeah, it just looks like, I mean, they don't look as ridiculous as I remember it. But, yeah, what if Babe Ruth actually hit 600? Whoa, was that okay? Sorry, Babe Ruth. Apparently, he's not even facing the outfield. What is he doing? What is Babe Ruth doing right there? Baseball players, landmark, home run, bat, fetches $1 million. Whoa. Wow. Wow. Find a Babe Ruth bat somewhere and sell that thing for $1 million. So, with this in mind right here, what our goal is to take the most relevant data. Does that make sense to everybody? We want to take the most relevant data. And so right here, we have the most relevant data, which is what people are going to analyze. And the biggest thing is, and I can't state this enough about these types of problems, is we are going to focus in on what the model currently says, because our goal is to predict the future. And what is our best understanding of the future? Events way in the past or events that are pretty recent? Pretty obvious right here, 100 points. Events way in the past or recent events? What is our goal for like predicting what will give us the best information about the future? Recent, bingo. Recent events. That's Joe. So good to have you commenting and everything. I love it. So the recent events right here, 100 points, all those answers. We want to use the most recent things to predict our new individuals. And here's the problem though. And I've seen this. This is a quick rant by Brian, very, very quick rant on this one, is that people make models that are too good. And what do I mean by too good? Like Julio goes in and he says, I can predict with 99% R squared, which would be 99% of the variation explained, on who will be successful in the majors. Now, if Julio can do that, which would be awesome, got to give him a lot of credit there. Julio's awesome. So maybe he can. Would they want to listen to everything he said? I mean, like, if he was just like, that person, like, he's just telling them, you hire that person, you take that person, you take that person, you give him this contract, you give him this contract. If he can predict with 99% success, like, or 99% of the variation in how someone will do in the majors, 99% of the variation, that'd be amazing. But a lot of times, we overfit our data, which means, and what does overfitting mean? It means the model works really well on which one of these? Overfitting would mean your model works really well on what? Overfitting means your model would work really well. It sounds like overfitting, yeah. Overfitting means your model would work really well on what? The training, because it overlearns the data. It learns like, okay, here's the patterns, and it fits perfectly through those patterns. So it would learn the patterns super well, and then it would not work on new data. So holdout is not new data. The holdout is a test of how it works on new data. So what does the holdout guard us against? The holdout guards us against overfitting. The holdout guards us against overfitting. And so someone could make a model that was based on the 1940 baseball players, which they had their own way of doing success, and they had their own, like, like, here's how you should run, here's how you should bat, here's how you should do this. And then they could say, like, wow, this explains so much variation in how someone is successful. But then when we take 2020 baseball players, the data is totally changed. And if we were to test that model, which is this when we do the test on the 2020 baseball players, we're going to see that it fails. And then what would someone do before using that model? So they would make a model from the 1940s baseball players. They would test it on the 2020 baseball players, because this is where we test to see if it works and we see how well it generalizes on new data, because this is going to be our estimate of how it does, or this is our test of how it does, rather. They're going to do what? Tyler's awesome. So good to see you, Tyler. What are we going to do right here? What are we going to do to the model then if it doesn't work? This is our biggest fear when we have overfitting. What are we going to do? What are we going to do? What are we going to do? Any ideas? What would you do with your model if it doesn't work? If it doesn't predict well on new data? Take your model, toss it out. Just baseball pitch, toss it out there. So we would toss out, make another one. I like that right there, Andrew. 20 points right there. Yep, make another one. We would rewrite it, modify things. It has to go back to the drawing board. So if your model doesn't predict on new variables, on new data, well, you can toss. This is not a good model. So here's the in-depth explanations that I was going into. Once again, these are on the notes if you want to see what's going on. So overfitting, all that good stuff. Terminologies, response versus predictors. Pretty easy stuff right here. What do we want to predict? Y. Y is what we want to understand. X is what we're going to use to explain it. So whenever you think of Y, you're asking, why does something happen? Why is a player successful in baseball? That is the response. The response is Y. I like to call X's explanatory variables. It's just my personal preference, because when I say X's are explanatory, X's explain. They're called features a lot of times. Not a bug, it's a feature. So this right here, you can call X's features. You can call them predictors. All these different things right here. Now, there's a lot of important things we're going to get into in these notes. These notes are pretty much like concentrated knowledge coming up here. So we'll go slower, but we'll need to know if an X is quantitative or if an X is categorical. That's going to dramatically change what type of model we make. Now, what's really awesome is the carrot package we'll be using will do a lot of this analysis for us right here. So the carrot package is going to do some amazing analysis. So let's start talking about some predictive modeling right here with the big pictures. We've got the evaluation metrics. Boom. This slide is concentrated knowledge, total concentrated knowledge. What is the difference between this and this? Was it Tyler I gave the crazy points to? I think it was Tyler. What is the difference between regression and classification? Who knows? Yes. What is the difference between regression and classification? I'm going to give someone 1,000 points. I haven't told you it yet, but what's the difference between regression and classification? Think for a moment. This is a huge thing that I wish I could just ask you as a written question. You should know this one instantaneously when you know it. Kind of. Jinning, I'm giving 1,000 to for the first good guess right there. I like it. We'll go. Hopefully I don't break something. Whoop. Sorry. Trying to go over here in the background. Who has the answer? I'm going to log in right here. Who has the answer? We'll see what answers people come up with, and I'll pick another answer for 1,000 points. We're fixing the world, Joe. Don't worry. Oh, gosh. Hope that didn't break anything. Okay. So what are people saying in the chat? Pretty much. Tyler are giving hints. Regression would be pretty... Yes, Jinning, you're totally right. You well earned those points right there. Exactly. No, they're 100% right. Is that regression is... You can do logistic regression. Some people, well, logistic regression. Well, that's a form of classification. So logistic regression is classification. But when we do regression, you have to know that this is a quantitative prediction. And when you do classification, this is a categorical prediction, like you're classifying items. So you're putting it into like the yes class or the no class, which Tyler was pointing out right there. Great job, Tyler. Good review right here. Classification is for a categorical, where regression is for a quantitative. So when you see regression, you should think quantitative Y. And when you see, I love the positivity of Stat Nation. So when you see classification right here, it's categorical. When you see regression, it's quantitative. So that's what we have going on, which is key. We should know what kind of Y we're predicting. Is it quantitative or qualitative, and qualitative being categorical? So there's a big difference here on the terminology we use. Now, this goes back to 320. 320 right here should know RMSE is the typical miss. I think it was Chow yesterday was saying, no, Xiao Ji was saying that they were like, yes, it was a good 320 review because RMSE is the typical miss. Congratulations, Tyler. Congratulations. And we have R squared right here is the percent of variation Y explained by the variation in X. And MAE is mean absolute error. These two are virtually identical. They're not. You're gonna hear a stat person say MAE is the best. Another one's gonna say RMSE is the best. And someone says no MAE, no RMSE, no MAE, no RMSE. So it's really a preference when it comes to MAE versus RMSE. And I think there's other ones. I think there's mean absolute percentage MAP. I think it's the mean absolute percentage error, MAPE. There's different measures. It's just how well is your model doing in the quantitative sense. So you can use any of these to gauge how your model is doing. What is the whole point of these right here? To evaluate our model. All of these are just evaluations. But you have to know which of these are for quantitative. So all of these here are quantitative. So everything right in this box is quantitative. And then everything down here is categorical. When we put things into categories, we're going to look how often we misclassify stuff, how often our model's accurate. And here's the one. Tyler and Joe will tell you, this is the tough one. This is the one people get stuck on. And they're like, I just don't understand it. And we will go over it a good bit. But AUC stands for area under the receiver operator curve. So this C right here is deceptive because it's actually an acronym within an acronym. So it's area under curve, and the curve is and then Joe knows that AUC is truly the one we care about. That's why I'm focusing on it. AIC is Akaike's information criteria, and Akaike, a famous Japanese statistician who gave us so much knowledge when it came to how to evaluate how close our model is to the truth, from 320, 100 points right there, Andrew. So AIC is Akaike's information criteria. He's a teacher to Humphreys Bosdogan, who's a statistician in our department. So Humphreys Bosdogan has Bosdogan. There, I think I'm saying it correctly now. He's a professor within our department and very, very, very knowledgeable man. I mean, brilliant professor. And so was Dr. Akaike. So this is AUC, which stands for area under the curve. What curve? The receiver operator curve. And it deals with your false positive, false negatives. I'll go into great detail on how this works right here. So Tyler and Joe know that quite well from taking 474. It's so good to see you swing by. Hang out, chill out, answer questions. My grandpa was an engineer, and all he talks about is area under the curve. Yeah. False positive, false negatives. Yeah. Jordan's totally right. This is and it's so easy to make because we've got code that just prints off this curve right here, and then you can see your false positive, false negative rate to see how well you're doing. Like you want the area under the curve to be 1 because the curve will be why not? Let's show some. Do we have it in the slides? Here, I'll show some right here. It's pretty easy to understand ROC curve. Let's just take a quick view of one right here. Here we go. There's a great ROC curve. So here's a really good ROC curve right here. Here's your random chance ROC curve, and that's a good ROC curve. And that red one's a pretty blah ROC curve. I mean, it's not as good as the other one. But what you want, this is great. Oh, good notes this person took. There's the perfect ROC curve. The purple one right here. And as I was saying, this is a random chance right here. And the more the curve goes out this way, the more area under the curve. Does that make sense that we're actually going to gauge this? And it's a 1-by-1 box. What is the highest amount ROC can be? These are great, final questions. What is the highest value for ROC? That should be just an instantaneous answer. Boom, Andrew, 100 points right there. It's 1. So the highest, because it's a 1-by-1 area. That was my Red Bull. It's a 1-by-1 box, so the highest amount it can be. By random chance, we should get ROCs close to what? by random chance with random things, we should get an ROC close to what? 100 points, everybody answering. Everyone chime in here. With random chance, we should get ROCs close to what? So look at the red line for that one. Random chance, we should get ROCs close to what? No one said the answer yet. Random chance, we should get ROCs close to what? 0.5. Caroline, nice job right there. Caroline's first. Yes, who else is going to get the 100 points right here? A half. Yep, because it's half of the... Yeah, so the random chance ROCs is this. I'll show you how to do this with the false positive rate and the true positive rate, and I'll work examples by hand. So I will work some examples by hand, and I will graph out the ROC. Not today, though. I want to get to more of the notes. Okay, let's hop back to the notes right here. So you can see some of these topics are pretty easy. Just memorizing. There is a R file that on Canvas has skeleton for a lot of the code that will run later in the semester when running AOC ROC. Yes, thank you guys so much. Goodbye, everyone. Yeah, goodbye. Good seeing you guys. And definitely 474. Look at the files. This is a huge help for homework and take-home files. Tyler. Oh yes. Tyler's talking about the. Let me show where that's at. Tyler, you go. And Joe, you should go look at. Did Joe not look at his points? Joe, you should have looked at your points. Joe, if you're still here, go look at your points. Let me show the file that they're talking about. They have well earned their points. So the file they're talking about is, I think it's this one. It should be this file right here. If you notice, this is under this. So it's kind of buried within here. It's this right here. Yep. And so there's a PDF on it, but I would rather go to this. And will that open inside of R? Let's see. Yes. I think we're doing it. Yep. And we need do parallel and plotrix. Okay, cool. This is the file they're talking about. Really crazy big file right here. And so this is the file that they're saying will be a huge help. This is the data mining using Caret, and we just started this. If you look at how big this file is, it's got tons of stuff in it. But you're like, okay, how would I possibly use this? I'll show you how to be using this throughout the semester, throughout the remainder. And it literally has headings. You could scroll through here and you could look through the different headings. But there's so many different examples of everything you want to do, like vanilla regression, regularized linear regression. Here's a random forest. Here, I'll show you again where it's at. The file is located right under modules. Under modules, so you want to go here. I'll show you the steps. You ready? Modules, go to modules. And then under modules, data mining 3. You know what I'm going to do? Watch this. I'm going to do something right here. Plus module, most important data mining file. Okay, watch this. Can I spell data mining? Sure. Add. Ugh, really? It puts it at the end. Let's go here to move module at the top. Did I do it? Okay, most important data mining file. Let's go here to using Caret. Move to. There we go. Okay, there we go. It should be pretty. Yeah. If you try, I copy paste it. Tyler, amazing advice from a former student right there. And Joe should look. Joe should look at your. Oh wait, did Joe? I love Joe's points. They can fight each other on their points, Tyler and Joe can. So we have right here, this file right here. This is super important. Tyler's definitely giving you advice from the future. Tyler's like, this is me from the future. Use this file. It'll help you through all the assignments. It shows you how to do everything. If you are doing a, let's say, random forest, boom, here's how to do the random forest. It has all the code for how to train your model. We were just talking about training the model. Yeah. And that's, yeah. So I'm so glad former students are here because they give the best advice on like, use that file, know what it means. And look, y tilde x comma data equals. Can we get some shout outs to 320 right here with a little y tilde x comma data equal? Now the newest thing we have after y tilde x comma data equal is method. Y tilde x comma data equals method. And what kind of method are we using right here? Random forest. So if you can't guess what RF stands for, it's random forest. And then we get train control equals fit control. The fit control was set up out here. So here's where this was set up. I'm going to put that to a separate line. Well, now I got to remove the append line. So this fit control right here is the train control for the model, which we'll talk about the k-fold cross-validation here later, but you have to know what's going on with this code. Like, you don't just run the code, you need to know that this is k-fold cross-validation with 5 folds, and do parallel just allows for parallel processing. That's what allow do parallel is parallel processing. The tune grid is how we're going to tune our model, and preproc what? Preproc is going to turn these into what? It's going to pre-process, and it's going to center them to a mean of 0, and it's going to scale them to a standard deviation of 1. Pre-process turns them into what's? 1,000 points first person. Pre-process will turn this into what's to kind of put everything on an even playing field. That way something doesn't have undue weight in the model. Boom, initial right there. You got it, z-scores. That part of the code will z-score it for us. So we don't have to turn things into z-scores. The function itself will do it for us. So if you look at each one of these arguments right here, we'll just break it into multiple things. 100 points, everyone else, initial, well earned. Great job right there with the z-scores. We have our y tilde x, which is our format. So this right here is y tilde x, and the x is all your variables. Data is the name of the data frame. Method is just method chosen. This right here, the fit control, the TR fit control. The fit control is how we do validation. So this is validation right here, if I know how to spell it. The tune grid is selecting model parameters. Should put comments on these parameters. You're welcome, Anisha. Great job. And then this is z-scoring them. I should have put the comments z-scoring. So, and this code won't run anymore. But y tilde x, that's the formula format for the y variable we're predicting and the x variables we're using. If x is a dot, you need to know this. If x is a dot, it's all of your x's. If it's raised to the second, it's all your x's with the allowing for the polynomial relationship. Please take a huge note. I've just dropped a ton of concentrated knowledge because this right here, as they were pointing out, is like the big code we're using for the remainder of the semester. And then you have to know what each argument does. Let's make very clear, this is a huge thing right now. This is the formula for model. That's the formula for the model. Y tilde x, we're predicting some y variable, whatever we put right there. And right now it's all the x's with allowing for the polynomial relationship between the x. It's going to have every x plus every x raised to the second power. This right here is data frame. The variables are in, so we have to give the right data frame. This is just method model is created by. We got to pause on this because here's where it gets insane. This is where it reaches absolute insanity. So we go to models in caret package. So here we go, list of all models. Here's your choices. If you're wondering what your choices are, so let's get some opinions. What do you think about the amount of choices you have for the models you can do in the caret package? Anyone got any opinions? You could do extreme learning machine, factor-based linear discriminant analysis. You could do fuzzy rules via, I have no idea what that is. There's so many. You could do generalized additive model using splines. Oh, do we not teach? I don't think splines are in the notes anymore. 2 semesters ago removed splines. Independent component regression. I don't even know what that is. I do not know what. Oh, whoa. What is this? Whoa, K nearest neighbors. We give brief shout out to K nearest neighbors right here. And there's 2 K nearest neighbors. I don't know why there's 2 different. They've got 2 different ways K nearest neighbors are done. I don't know why there's 2 different K nearest neighbors. What are the most used? We go over those like logistic regression, linear regression, regularized regression, random forests. The ones we use in this neural nets, support vector machines. So you could do here support vector machine, and here's different types of support vector machines. You could go to, it's a random forest. So you go here to random forest. You see there's a whole bunch of different random forests. So we kind of teach like the different global topics. You could go here to regularized. We teach what regularized is. So anything that's regularized here, like a Bayesian regularized neural net. So I know what Bayesian models are. I know what regularized models are. I know what neural nets are. So I have a decent understanding of what a Bayesian regularized neural net is. It's pretty complex, but you can run a Bayesian regularized neural net with this. And it's pretty easy as long as you know the theory behind what it's doing. You could create this using the carrot package. There's Deep Boost, which is going to be a neural net. It's boosted trees. Sorry, these are boosted trees. So I know that a boosted model, so we should see here boosted trees. There's extreme gradient boosting. Yeah, so it's boosted tree models, ADA classification trees, ADA boost classification trees. So I know we'll teach boosted trees. So by the end of this semester, you'll know what a boosted tree is. Boosted trees are trees that learn from trees. So when we know this right here, we will learn what all of these mean. So that's what we have going on. Very important to know what all of these models are. Does that make sense? We'll be learning what these different methods are, and then we will learn about validating our models. So let's learn about validating our models. And then we'll learn how to tune our models. And then, of course, we z-score stuff. This, if you understand all of these steps and why we do them, you maybe understand 40 to 50% of the remainder of the semester. But these are all big topics, and we don't just write the code to write the code. Everything I have right here, I know why it exists, and I know the theory of why it exists, and I know why we're doing it and what it means. And then this part right here is really where we'll spend a lot of the semester talking about like the different methods, because every method has its own parameters we would pick for it. And what are you going to do? Think about this. Let me explain it this way. When you bake a cake, what are the parameters we have with baking a cake? What are the different parameters we can adjust for when baking a cake? So the parameters in a model are the things we adjust for that control the model we make. So what are the parameters we get when baking a cake? I actually do it instead of R because I can do it a cool way instead of R. So what are the parameters we can adjust for when baking a cake? Temperature. So let's go here and go temp, and let's bake a cake at 303. You know what we do? Watch this. Sequence. We're going to bake cakes, and we're going to bake a cake at 300 to 450 going in terms of 50 degrees. So here's the sequence right here. The sequence has length 4 because it starts at 300. All this good stuff right here. There's temperature, amount of ingredients. I like amount of ingredients. Baking time. I like baking time better. So let's say time. And time is going to be a sequence going from 15 minutes to 45 minutes going right here. Cool. So that's the time vector right there of how long we'll bake it for. Amount of flour, shape of pan. So let's go to shape. Let's put in here oval. Let's put in square. Those are the only two shapes I know. The flavor. Oh, I like that right there. That's 100 points flavor. Let's go to chocolate. We need one more. We need something more dealing with taste right here. Let's go to strawberry. Let's go to cookies and cream. Oh, God, got some good options. What else do we have? I'm going to go with icing. So icing. And let's go here to icing. And under icing, we will have we'll go to chocolate, cream cheese, and let's go to none. Some people might want icing. Icing, fun, confetti. Casey, 100 points right there. Confetti, that's a flavor. We got that. I like funfetti. That's one of my favorites. So, and we're going to here cookie. It's cookie flavor. Okay, so we've got all these vectors right here. Let's go to this. Let's go to expand grid. And let's go to temp, time, shape, flavor, not factor, icing. There you go. Somebody pick a number. Let me look at here. Grid. Let's just call this grid. Somebody pick a number 1 through 672. Somebody pick a 62. Casey, your cake is going to be the cake was cooked at 350 degrees for 20 minutes. It was in an oval pan. You get strawberry cake with chocolate. Everyone's picking low numbers. You can pick this 672. 43. You get a square cake cooked at a higher temperature a long time, and it's cookie with that's a really good cake right there. That sounds like it's cooked for a decent amount of time and everything. So you know what we need to do? We need to add one more thing to this. We need to add I don't know. What else could we add to it? We only got a few answers. Someone's got to give out 333. I like the 333 right there. I want to go to the higher cakes right there. So you get a square strawberry. Oh my gosh, Nitin, I think it's cooked for 45 minutes, so it might not be as like, I don't know, maybe that's the perfect time to cook a cake. It might be, but if you look, what is this expand grid giving us? The expand grid is giving us every combination of cake we could make. So let's go to 101. I know, right? It might be. I don't know. I don't bake cakes. There, we got a chocolate strawberry again in a square pan. Let's do one more right here. We've got a strawberry cream cheese. Oh, this might be the winner. A square strawberry cheesecake. Cheese 474. Yes, Ahmed, great answer. 100 points, Ahmed. That is the right answer right here. It's just a cookie cake. It's just a cookie cake. How about a cookie? Yeah, there we go. This is just a cookie cake. Ahmed, that's worth 100 points. That's because I like that cake. So we have here the perfect cake. So if you look at this, what have we done with this expand grid? We've controlled for all, we've manipulated variables, and we've done all the combinations. Here's the thing. In regression, how many regression models do we usually make? In regression, how many regression models did you make? I was talking about this last night in the Discord. How many regression models do you usually make in regression? When you make a regression, you usually do what? You make how many regression models? You make usually how many? Like when you're making a model, not like in terms of the class. But in regression, when you make a model, you make how many models? I've got the answer hidden away behind the screen. The answer is... No one knows it? Well, you got the answer. Who knows it? In regression, you usually just make how many models? One. You make one model. You usually make one. So here's my regression. You say da 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 da. You do that. You go wait. You go data equals survey 10, not data minus. That's going to be mad at me. I'll do that. And then you say run my model. Oh, good. We got it in here. You say make the summary of the model. And you say I'm good. There's my model. I'm good. I'm ready. Ready to do the analysis. And with this right here, you made your model. You're done. But in data mining, how many different cakes are we going to make to try out right here? First person, 100 points. How many different cakes would we make? Which is basically making models. We're going to see which of these is the best. And we're going to have some way to analyze via a metric. Oh, perfect slide right here. To assess which of these models work and how many cakes. We're going to make all of them. I like that right there. 100 points, Andrew. We're going to make all of these. So this is what data mining is. People ask me, a few people ask at the start class, like, what's data mining? Great question. It's the ability to look through and make models beyond just making one model. It's making tons of models and then assessing those models and finding better models based on a higher computing power. We couldn't really do. What about the cost? Oh, yeah, okay, ooh, you've literally just hit on design of experiments. Is that what my books are? It's process control. Process control now also has some design of experiments in it. All items donated. Casey, 100 points right there. I like the comments. So Nitin also 100 points because Nitin brought up the real world scenario that if this was a designed experiment, that companies like Eastman would maybe say, we don't have the time or money to run all of these. And that's where you get into, I haven't taken DOE in a while. You get into an incomplete design. So you could actually optimize your design by choosing certain things right here. So in a designed experiment, you would use an incomplete design where you wouldn't do everything, but you could capture the variation within the variables by making the proper designed experiment, which designed experiments would optimize how many. So they might say we can get the coefficients for these by only taking in, we could do 60 different cakes. So I should really do more DOE. I don't teach the class. I haven't taken it in a while, but I do understand how you would use a designed experiment to capture the variation. Now, so this example is a perfect DOE example, but here's the good thing. So Nitin, your point, when it goes over to regression, when we make our models, all that matters is the cost, is the computing power. So we're not actually going to make the cakes because that'd be a designed experiment. For us, we're going to let the model look through the coefficients. And if you notice, if we go back to where we have this screen right here, you can see the different parameters. So here's the tuning parameters, does this make sense? This would be things like the time or temperature. And some models have more tuning parameters. And if you have more tuning parameters, what will happen to your expand grid? If you have more tuning parameters, I wish we could find one with like 8 tuning parameters. It'd be the neural nets. Neural nets have a lot of tuning. Neural network. There we go. Look, this one has 7 tuning parameters, and there's ones with more. If you have more tuning parameters, you'll have more whats. If you have more tuning parameters, more things you can kind of adjust for your model, your tuning grid will get much wetter. More, because watch this. Let's go back to here. If I all of a sudden add in, let's add in, we're gonna have levels to the cake, and it's gonna be either a 1 level or 2 level cake. So now we're gonna have levels. How many different cakes will I build now if I add in levels? Hint, you can figure it out with that. 1,000-point question. This is definitely on the final. How many cakes will I build now? Oh, replicates. Ooh, you might be talking some DOE right there with replicates on like, yeah, that's some DOE talk. Have you taken DOEs, Casey? If you have, that's DOE talk. Bingo, Nitin knows. Yep, exactly. Nitin, well earned 1,000 points. If you look at the expand grid now, that's the exact answer. Yeah, replicates would be like a replicate on a cake, which would confirm that it would lower the variation. We could check a lot of things like linearity of model, and that's some good DOE talk. So Casey right there, 1,000 points. I haven't heard replicates in a while. That's a DOE talk term right there. But a repeated cake. So we could have some replicates to check for variation within cakes. So that'd be the within variation. Like, yeah. Problem is, if we're doing this, we have a judge variation too, because variation is going to come from our judges, not just our cakes. So this would be a complex model on what is the best cake, but we could try to narrow it down by doing a designed experiment. Does anyone else watch King of Random? I got a bunch of favorite YouTube channels. They were testing popcorn recently in one of their videos, and they were testing 3 different types of butter. They were testing lard, coconut oil, and canola oil. So they were testing making butter in 3 different types of oil, and there was 2 different testers. The man and the woman were testing it. Grant passed away. I don't know the names of the people. I only know the guy. Unfortunately, he passed. Maybe, I don't know. But and really sad what happened to him. But they were testing the popcorn, and it was 2 testers. And then I was also wondering how long were they letting the popcorn sit out after eating it, because what sounds better? Popcorn that's been sitting on the table for an hour, or popcorn you popped 5 minutes ago? What sounds like, if you're like, man, Brian, oof, that'd be good right now. Like, you're about to watch a movie. Do you want popcorn you popped 5 minutes ago or popcorn you popped an hour ago? What sounds better? 5 minutes, because you kind of got that warmth in the bottom of the bowl still. It's not too hot. It's not like it's just out of the bag with the steam coming off of it. But that 5 minute ago popcorn, that's great. So I'm like, wait a minute. They need to control for that variation. And you probably want if you were to get crazy on this, you would have like a popcorn with mini M&Ms. That might be good. So thank you, 20 points, all those answers in the chat, because you'd want to control for this variation. And with only 2 people testing the popcorn, also, were they using the same kernels from the same, there's all this variation. This is all, and I love their channel, and they're not doing like stuff to change the world. And they're not like coming at it from a statistical aspect. They're kind of just doing an at-home experiment. But then statisticians are going to go like to the extreme, looking at all the variation and trying to control for it, and being like, okay, we have to know where the variation is coming from. Is it the oil? Because think about this: is it the oil that makes them like the popcorn better or worse, or is it the time after pop that makes them like the popcorn better or worse? Because especially with oil, it might settle on the popcorn differently. Like popcorn that's been popped after 5 minutes versus popcorn that's been popped after an hour is going to have a different type of oil coating, where the 5 minutes might have a more like shine to it, and the hour might have more of a slick taste to it or something. If you get what I'm saying, if you ever had popcorn after it's been out for a while, you're like, oh, the oil's kind of congealed on it. It's a weird topic. But that's variation. It's variation. It's a parameter we would need to control for if we were doing this in a designed experiment. So if you can't tell, let's hop back to the main screen here. No. I don't know why things take a moment sometimes, but we need some way to analyze what is the best. And if you were analyzing popcorn, you'd be analyzing things like, what's the taste score of the popcorn? And then you would want a model that explains, you would probably be doing, if you're doing taste score, you'd be doing regression. So you'd want a model that explains the variation. So you could use R squared to say, like we were able to explain this percent of the taste score via the oil that was used, the amount of time it was left out, and also maybe the taster, because there's going to be between ranker variation. So hopefully you'd have a high R squared. You also would have RMSE, which would be like, we can accurately, or when we predict the taste score, we're typically off by this amount. Does that make sense what the RMSE for the taste score of the popcorn would be? When we predict taste score, we're typically off by this amount. Like we say, okay, we predict this will have a taste score of 8.9, but we're typically off by about 0.3 in the taste score. So I don't know, it might be about 8.6 to 9.2. Does that make sense what RMSE is? It's how much we're typically off by. It's not how much we will be off by. But when our model makes predictions on a quantitative Y, it's about how much we'll be off by. It's like, we could be off by about this amount. It's a kind of like just think of it how you would talk to people. Oh, I'll be there at about 5, but maybe about 5 minutes off from that. So are you saying you'll be there at 5:05? No, I'm saying I'll be there at 5, but I don't know, within 5 minutes of 5. Does that make, that's what RMSE is. It's like how we talk in our everyday life. I'll be there at 5, but maybe I'll be off by about 5 minutes in my estimate. Doesn't mean you'll be there at 4:55. Doesn't mean you'll be there at 5:05. It means your best guess was 5, but I don't know, about 5 minutes off. Now, when you tell your friends that, do you sometimes show up at 5:06? When you tell your friends you might be off by about 5 minutes, do you sometimes show up about at 5:06 instead of, you say 5 and then you show up at 5:06 and you're like, oh, I might be there, I don't know, within 5 minutes of that. Yep, all the time. Because you're not saying it will be 5 minutes or up to 5 minutes. You're saying, typically when I make this guess, I'm off by about 5 minutes. So maybe a little bit more, maybe a little bit less. I don't know. It's sometimes 5:30. And would that be very unusual? That would be very unusual because that's 6 standard errors away. So when you look at this right here, that's basically kind of like a z-score of 6. And your friends would be like, you said 5 minutes, it's 5:30. If you showed up at 5:07, that would not be too unusual. But 5:30 is pretty unusual for that small of an error. Like if your typical miss is about 5 minutes, a miss of 30 minutes would be a very large miss. Does that make sense? If your typical miss is 5 minutes, a miss of 30 minutes would be a very large miss. So that'd be unusual right there. We'd say, that was weird. You'd say, what happened? You'd be like, oh, I traffic jam. And if someone shows up at 5:07, you'd be like, oh, well, that's about how often they're usually off. I'm usually early. There we go. So your typical miss, well then, yeah, you'd have to change your guess. There we go. And so classification, when we do classification, when we talk about the misclassification rate, it's the percent of time that we misclassify an item. So if we're predicting if somebody will like, let's do the coconut oil butter versus the canola oil, because I don't know, the lard just did not sound too appealing to me. Has anyone ever had like stuff cooked in lard? Someone tell me the benefits of that. It just, the word lard, which you shouldn't, what kind of good argument is a word does not sound appealing? Let's just call lard amazing. Have you ever had anything cooked in amazing? Which is funny. They'll sometimes rename stuff to make it more appealing. But if we were to do the canola oil versus the coconut oil, but there's going to be interactions, like are we doing a sweet or savory popcorn? So if we were to say, do people like the popcorn or not, we could make predictions on whether or not people like the popcorn. Does that make sense? So now we're no longer doing regression. We're doing classification if we're predicting, will somebody like this popcorn? So then we're going to predict yes or no for somebody liking the popcorn, and we'll get a misclassification rate. You want your misclassification rate to be what? What do you want your misclassification rate to be? You want all of your misclassification rates to be very, very what? Low. Ginning, 100 points right there. And you want your accuracies to be very high. Now, these two are complements of each other. If your misclassification rate is 10, boom, want it to be 0. Like that right there. If your misclassification rate is 0, your accuracy is 100%. Accuracy is the percent of time you accurately predict what somebody wants, and misclassification is the percent of time you don't predict it accurately. So they're just complements of each other. So this could be called non-accuracy. I don't know. This is classification rate, and this is misclassification. AUC, we will go into a lot more detail as time goes on, but you say, well, why don't we just use, and then precision, those are terms, and we do talk about those a little bit because I can't think of the terms because there's false, not positive, false, negative, true, positive, true, negative, all these terms, and a lot of disciplines go into like, we want a very high precision, all these things like there. So you'll see that in the literature too. And AUC is where I really stand by. I use AUC a lot because AUC looks at the false positive and the false negative rate, and it's seeing how quickly we can get all the true positives here really quickly. Kappa is used, but I don't use Kappa that much. You might use Kappa. We'll show it in the notes. Kappa won't be on the test. I show it just so you can see it. I don't think it's the best measure, so I don't use it, but it appears, so you'll see it, and it's a good reference if you see Kappa or you want to use it. I don't like it. Here's the definitions of these things. So if you're looking for more, just reading through, just practicing, reading over these, awesome. I don't like reading slides. Generalization error. We've been talking about this, and if you can't tell, these are the big things you need to know right here, is that when you have training data, this is what our model learns from. You need to know this instantaneously. This is our training data, i.e. when you're in the train function, we should be able to make this small window. Small window, there we go. When you're in the train function, you will see the first thing right here is your data you're learning from. So the reason this function is called train right here is because it's going to train the data on this. More on train control in a bit. The holdout sample is only used to evaluate the model. So I want you to think about this. What you're going to do is you are going to have, and we could even talk about the popcorn with this. You're going to maybe make a model that explains what people think about popcorn by making popcorn batches and then training, like learning the different variations. But then you're going to have batches of popcorn that you have that then you're not going to make a model from. You're just going to see how well your model works on. So you're not going to have people eat this popcorn here. So let me go to the training data. If we were to talk about this with the popcorn examples, the training data is literally you have people eat the popcorn and you have them give numbers and then you figure out the variation that explains why people like popcorn. So you're going to learn from the training data. But then with your 100 bags of popcorn you made, you held out 20 of those bags. So these 20 bags of popcorn you made here are not going to be used to explain what people like about popcorn. They're only going to be used to see how well your model learned. Does that make sense? That here's where we learn about our data. Here's where we see how well we've learned. So the holdout is literally making 100 bags of popcorn and taking 20 of them to see later on how well your model understands what people think about popcorn. So you won't use that to like understand the variation. You'll just use it to see how well you understand. This is the key concept. I can't state that enough. Do people think they understand this right here? That the holdout will not help us create coefficients or be like, oh, looks like people like coconut oil better. Or, oh, it looks like people like it cooked for 3 minutes instead of 2.5 minutes. We're not going to use the holdout for that. We're going to use the holdout to say, how accurate are our predictions on data that our model did not learn from? How accurately do we understand the variation within this? And we will only use it for that. And how do we get the holdout? We literally take part of our data and do what? Anyone have any idea how we get our holdout data? We take our data, here's all of our data, and how do we get the holdout? We take some of our data and do what to it? What's the word say? How do we get holdout data? We take the data and what? 100-point question, who knows? How do we get that holdout data? It's like it's like what? How would we get it? We extract it, we hold it out. And we're going to randomly sample it too, both of you right there. Grade it. How are we measuring the accuracy? If we're seeing like a taste test, if people like, if we're doing a taste test of popcorn, the way we would measure the how well the model predicts taste test is probably going to be this. If we're doing taste test of popcorn, I would use this right here because a taste test is a quantitative thing. So we are going to use RMSE for taste test, I would say. If we are doing, do people like the popcorn? Like we go to a grocery store, we're going to say like, do you like this popcorn? I'd probably use AUC right here. So if we're going to ask people, do you like the popcorn? We're going to measure how well the model does based on the AUC. Higher AUC is better. So this is for, do you like the popcorn? And this is for, give the popcorn a rating 1 to 10. Just depends on how we measure what people think about the popcorn. So we'll try to optimize probably RMSE here. You could use other things. They're all in the literature. But RMSE is what we typically use. And then down here is, do you like the popcorn? And then we'd use AUC for that. So we're going to optimize these things. So great questions, amazing questions today. And so here we go. We see it instantaneously. So here we go with the train and the holdout. Take a look. And Anisha pointed out we're going to get them randomly. So we are taking right here 30% of our data. Wait, Brian, that's a 70. Well, that's the data we're putting into the train rows. And once again, as Tyler and them were saying, you can just literally take these lines of code that create for you your training and create for you your holdout, and you can just copy these lines of code. This will randomly sample 70% of your rows to be train rows. And then when you take the train rows right here, that'll store them in train because you're taking census only the train rows. And holdout, you're taking not the train rows, which is everything but the train rows. So you either take the train rows or you take not the train rows. Not the train rows is the holdout, and the train rows are the train rows. So very important we see what's going on right here. Here's a linear model being created with every x to the second power, and it also includes each x itself. And guess what we get right now? We have the RMSE. So the RMSE stands for the root mean squared error. And Ahmed, that is such an amazing question because the answer is meh. It's due to the structure of the data. I'd probably say for data that has more outliers, you should have a larger sample size to make sure your holdout and train have a similar structure. So that's such a good theory question, and the literature probably says between 20 to 30. Dr. Seaver likes to take 5 holdouts. So that way he can test his model on 5 subsets of data and then get an average generalization error. So Dr. Seaver's practice is to take 5 holdouts. So he would literally run this code right here and create 5 different sets. I guess you could create 5 holdout sets and then it'd be a more complex code, but you could create 5 holdouts and then test your model on 5 different data sets that have been held out. Now, this is, of course, if you have a decent sample size, because you wouldn't want a holdout to only have like 3 observations in it. So if you had 30 data points, maybe I'd hold out 10. Does that make sense there, Ahmed? So if you had 30 data points, which is a very small sample, I'd maybe hold out 10. If you have 1,000 data points, you could hold out 400. And you could do like, you'd hold out 500 and do 5 different. And it's model dependent. Because it's how much data do you have, what's the structure of your data, and it's a really tough question. This is why predictive analytics is not easy. Making good predictive models requires a lot of knowledge of how the data is, and then testing your model, making sure it works, and then it's all question dependent. And so what we see here is the RMSE. So think about what the RMSE of RMSE is. The M of it is it's mean, and the R is root. So there's your root mean squared. And the error right here is just a what? Hint, it's the actual minus the predicted. 1,000-point question, 320 review. We're not done yet. Don't leave. 8 minutes left. This part right here is the actual minus the predicted. That's just the what? I'll accept 2 answers, 2 possible answers. It's the actual minus the predicted. What is that? It's the actual minus the predicted. It's the what of our model. I'll take that right there. Anisha, amazing points today. It's the error. It is the error. It's the RMS. It's the E of the RMSE, which stands for residual. It's the residual in the model. So it is the RMSE. Casey also 1,000 points, like you chiming in right there. So giving out some crazy points. Stay till the end every day. Make sure to keep working. 100 points, everyone else. Thank you for staying till the end right here. So the RM squared error. So this is the error part of it right here. It's the actual minus the predicted, which is a residual. So just doing different RMSEs. Right there. And the observed over the expected would be a standardization of an observed. That would be an F statistic oftentimes, or a discrepancy. Jordan, good job right there. 100 points still. Observed over expected is a standardization of what you observe. So that's going to be a discrepancy, or an F is a discrepancy. So an observed minus expected square of expected is classic chi-squared. So good review of that. Yeah, there's a lot of random things to keep in your head. Generalization error is how we see how it works on new individuals. We've said this like 3 times today. So whenever you think of generalization error, your goal is that the model works on new individuals in the long run. That's the whole goal of this. We can never directly observe the value. We can only compute this error. So we don't know what it is. We just make an estimate of it. So the holdout is just our estimate. But what do we have that estimates how it'll work for our estimate? We have the estimated generalization error. And I think this will be next. And I think we're going to get into this, and we'll start this more tomorrow. But this is a big topic here, the k-fold cross-validation. And that appears right here. This little bit of code, this one line of code right here with method k-fold, so that's k-fold cross-validation right there, is where we're seeing this appear in the code. And I think that's what we're talking about next. Yep. Let's start this up. We'll continue it tomorrow, but don't leave yet, because this is how we use the k-fold cross-validation, which, remember we talked about we have our model, we have how it generalizes on new data, but now we're going to estimate how our model generalizes on new data. So please note, your model, how it works on the data it was created from, is from the what? Is from the what? What portion of your data? How your model works on the data it was created from is your what portion of the data. 100 points in the chat. How your model works from the data it was created from is the what portion of the data. Training right there, Jinning, great job. How the model works on new data is the what. Is the what. How the model works on new data is going to be the what sample. I need to say there. The holdout. I think we'll start saying in a second here. The holdouts. This is how it works on the data it was created from. This is how the model works on new data. And now we're going to estimate. So think where Brian's in the middle right now. We're going to have a go-off point for where how we estimate it'll work on new data. So we have how our model works on the data it was created from, how the model works, how we think the model will work on new data, how the model actually works on new data. So you might be wondering, why are we doing this? I might be able to explain a little bit today. Got 4 minutes, enough time to start talking about it. The k-fold cross-validation process, which is key here, is going to split our data into k chunks. Every time you see k is just a placeholder, like with k means or k nearest neighbors. It's how many nearest neighbors are voting. It's how many means we're using. It's how many chunks we're making for the k-fold cross-validation. Now, what we're going to do with this is we're going to create a pseudo holdout. Now, pseudo means fake. It's not going to be a real holdout. And we're going to then make our model on the non-holdouts, and we'll see that visually here. I think it's next slide. Here we are. So here's where your model is created, and here's the pseudo holdout. So this data is held out, and this is k-fold 4 because there's 4 folds. And what we do then after we make the model here, and we see how it works here, is we then move the validation to a new chunk, and we make the model with this data right here. There's where the model's made from. And then we test the model here. Then we move the validation chunk and we make the model with this data right here, all the data that's inside of here, like the different just values. So this makes the model. And then we test the model. And then we make the model with here right here. And then we test the model on that portion right there. So what is this doing? It's actually using everything inside of here is all technically what data? Every single thing. And this is like the rounds we go through. Like this is the data. Like the data is the same data here as the same data here. It just is a different round where we repeat the process. We iterate the process. So every single observation here is technically inside of the what. Every single thing is inside of the what. Every single thing, it's all inside of the train. Everything here is inside of the train. It's all training data. It's just that at one point we make a validation portion. So this is all training data. But we make a pseudo holdout. This right here, this validation is the pseudo holdout. It's not actually a holdout. Because how many times will this portion of the data right here that I've highlighted here, how many times will this portion of the data help make the model? How many times will this portion of the data help make the model? This portion of the data will make the model in the k-fold 4. That portion of the data will make the model how many times? 3. It'll help make the model 3. And then it'll act as a pseudo holdout, not a real holdout, 1 out of the 4 times. So it's held out in 1 out of the 4 times. So it's still used to make the data 3 out of the 4 times right there. And it gives us an estimate of how it'll do. And we just repeat this process going through. It typically underestimates how it'll work on new data. Like it's going to be nicer to us because, I mean, it's actually using the model that the data makes the model with. The values of k is a choice. You can pick whatever. Smaller goes faster. Yeah, you can pick whatever k you want. I don't know. I've never done anything ridiculous like k-fold 100. I don't know how that would work. So if time allows, the k-fold cross-validation can be repeated. This will be our last slide for today. So this is a repeated CV. So you should just be able to go over here to R. And we should just, oh, you have to put in repeats then. You can just change this to repeated CV, I think it is. I oftentimes just use CV. But and they have to go in here to repeats. It would have an argument now repeats. So you just change the method right here to repeated CV instead of just k-fold. And when we do this right here, we get an estimate, and you also get not just a mean miss we would have, you also get a standard error. Well, you could if you wanted. So you can get the typical miss you'd expect the model to make on new data, and you could get some variation within it. And that does it. We were going to start tomorrow with the k-fold cross-validation, and we'll have a tricky slide like this that definitely people get confused on. This slide right here is one where people are like, I have no idea which model I would pick. And I'll say, we picked the model that the validation says we should pick. Which one of these? We'll do office hours, we'll do questions right here. What model, you can describe in words, what model. Imagine this was on the test and it said, model in the top right, bottom in the bottom, model at the top, model at the bottom, model at the far left, model at the far right. What model would the k-fold cross-validation have us pick? The model at the top, the model at the bottom, the model at the left, the model at the right. Which model? We're done with class. These are slides I'm just talking on for a moment. I'll review this tomorrow because class time's over. Far's left. Yep. So this is the model you would pick, and this is how we estimate it'll do on new data. So this is our estimate of how the model will do on new data. Oh, no. Oh, my gosh. Sorry. That was an error. That's what happens when Brian tries to do a slide. This is our estimate of how it'll do on new data. That's the point we pick, and if you drop a line down, that's how we estimate it'll do. And then the holdout is how it actually did on new data. Does everyone understand the key difference? That if I go down, this is how we estimated it will do. And then the going to the left is how it actually did. But we're still picking the model with the lowest estimated generalization error, which is from the k-fold cross-validation process, which estimates how our model will work on new data. And then the RMSE holdout is actually the generalization error. This right here could just read generalization error because that's how it does on the new data. The holdout is the new data. So this is how our model does. So what model does the best? Top left. I think they're actually nailing. What model does the best on new data? Far left, far right, top, or bottom? What model does the best on new data? What model does the best on new data? Top, bottom, left, right. What model does the best on new data? Any ideas? 100 points, who knows? 100 office hour points. These are additional. So the one on the far left is the one that we think will do the best because it's the furthest left. That's the one we estimate will do the best. So does that make sense? This is the one we estimate will do the best on the far left. That's when we, due to the k-fold cross-validation process, we estimate that this one will do the best. But the one that actually does the best is where? The one that actually does the best is where? Where's the one that actually does the best on new data? The one that actually does the best. Here's a hint. Where's the one that actually does the best? Yep. Those are the ones that actually do the best on new data because they have the lowest error on the holdout. So you wouldn't pick these models, though, because you pick your model based on your estimate of how it'll do. You don't, because I'll talk about this more tomorrow. When I say people say these things to me, it's what I literally have thought. Why would you not just pick your model based on how it does on the holdout? Why not just pick the model that does the best on the holdout? And it's a key term. And I wish I could have you write an essay on this, or at least like a sentence response. Why not just pick the model that does the best on the holdout? I thought that a long time ago. I was like, just pick the one that does the best on the holdout. Why not just pick the one that does the best on the holdout? I'll let you think about this for a moment, then I'll give the answer. But it's a key thing with predictive modeling, and it'd be a horrible idea to do that. To pick the one that works the best on the holdout. You wouldn't want to pick the one that works the best on the holdout because you might have done what? Kind of. You might do what? If you just pick the one that works best on the holdout, how would you know you didn't do this? How would you know you haven't? I gotta go back slides. If you pick the one that works the best on the holdout, how would you know that you have not overfit? Because if you pick the one that works the best on the holdout, you're just optimizing the holdout. So how do you know that your model actually works on new data if you purposely pick the one that works on new data? You'd be like, well, it works on new data. Well, but you picked the one that might be overfit to it. How do you know that? So do you know what we do? We pick the one that we think will work on new data. So this right here is how we think it'll work on new data. Does that make sense? This is not at all from the holdout. This is how we think it will do. So we pick the one that we think will work the best. That's the one we think will work the best. It has the lowest estimate. And then we have no idea how to work on the holdout. When we test this model right here that we pick, we have no idea how it'll work on the holdout. We don't know. We're like, well, let's see how it works on the holdout. And what would we want? We would want its holdout error to be similar. Now, this one does have a higher. It's like at 4.2 and it's like at 3.85 or something here. It does have a higher RMSE than on its holdout, which is what we generally see. If you notice, a lot of these have higher, like there's very few that have lower, that do better on the new data than we thought they would do. So once again, we don't pick the one that does the best, or else we could just be fitting to the holdout. So you don't just fit everything to the holdout and say, okay, let's pick on the holdout. Well, what's the whole point of making models that try to create the coefficients for you if you're just going to put the model on the holdout? And the holdout has less data anyways. It's just a test. The holdout is just the test to see how you do. Who feels like they understand that? Because that's a huge concept. And I didn't understand for a while. Like when I first took these classes as an undergrad, I was like, you should just fit on the holdout. That's the whole goal. We're trying to see how it works on new data. So let's just make it work on new data. Well, but then how do you know it works on new data? The holdout is data it's not supposed to see until you give it the final test. And you only give it one final test. You say, work on this data. And if it works, you're like, yes, it works on new data. You don't let it look at all data or all models and say, let's pick the one model that works. Because if you do that, you're just trying to fit your model in a way that you shouldn't. And that's definitely the bad utilization of statistics. There's so many people who the use and misuse of statistics. Here's the thing, my last rant on this. Okay, so T is the problem of overfitting that we want to avoid. Yeah, overfitting is a huge problem. Overfitting is huge. And the problem is that like there's the saying publish or perish. So a lot of people will try to find results. Like they'll just purposely like search for results. But then if you look at it, something like Eastman isn't trying, nothing wrong with publishing, but there's just this need to find results sometimes. And then there's a lack of replication in scientific research where it's hard to get funding to be like, I want to replicate someone who found this out. I want to just redo their research. And they're like, oh, they already did it. Why are you redoing it? So what we get is if people are purposely trying to find results, are they finding results or are they finding p-values that are low? Like, watch this. Let me show you. I'll find some low p-values. Random chance p-values. Here we go. So I'm going to create random chance p-values. To create random chance p-values, yeah, I wish we did more replication in science. That's a issue. Like, science is great. Science is excellent. I'm not bashing science. The only problem with science is we need more science. Like, the issue with science is more science is needed. And so replication and stuff like that of scientific studies. So here's some p-values right here. Let's go to uniform. Oh, wait, random uniform. Random uniform prints numbers 0 through 1 in a uniform fashion. If a p-value is random, it'll be anywhere between 0 and 1. So we're going to make 10,000 p-values. There you go. There's 10,000 p-values. So watch this. Min of 10,000 p-values. I just ran 10,000 results, and there's a p-value. This p-value is completely what? I wish I could press the button. That p-value right there is what? I just did 10,000 I just did 10,000 tests. And I could do that. I could have a computer go through and analyze different ways variables are connected. I just did 10,000 tests. That p-value, though, is completely and utterly what? Keyword right there. That p-value I obtained is 100% random. I got that by random chance, and that's a pretty awesome p-value. I mean, I see p-values much higher than that in research. It's completely random, but I ran 10,000 tests. We could up this to 100,000 tests. Oh, look at that. Now it's ridiculous. And with computing power these days, you can run a lot of tests. I mean, it just depends on the data. How many variables do you have? What kind of tests are you running? But now the p-value is, if you can't see, it's 0.1234567 I mean, this is the dream of people who are trying to put out research to get a p-value like this. and to be like, whoa, look at that p-value, it's amazing. But the truth is you got that p-value randomly. Now you wouldn't really know that. You wouldn't be like, oh, I bet I got that p-value randomly. But this one is completely by random chance. I mean, just generate another one. Generate more random p-values. Oh, that one was really good, that first one we got with the randomness. Am I ever going to get one that low? Wow. First one was the best. I want one with negative 0.8. Really? Oh, maybe it only generates to that many decimals. We saw another 0.7. You know what you could do? I'm doing this. I don't care. I'm going to generate, because what does everyone think I'm going to do? I want to do this 10,000 times. I want to generate 100,000 numbers 10,000 times. So what am I going to do? Let's go here to min and store into here blank vector. And we're going to go here to min position I. And min position I will have this. We're going to go to the mins of mins. I want to see if it, oh, haha. Didn't put that. It's like, what's the error? I 1 through 10,000. Okay. So now we're getting, we're doing the minimum of 100,000 values 10,000 times. It's taking a little bit longer than I thought, but it should be able to do that. Unless I did something wrong. Taking way longer than I thought. But this should get us the min of this right here. Isn't that we look for a high estimate value than just a small p-value? Yeah, you want to look for the practical significance of it. Maybe I crashed R, hopefully not. Which I did not think this... Oh, there it goes. It's like, that shouldn't crash it. But you want to look for... A lot of times in research now, they want a good effect size, which I've heard a lot of scientific papers saying we need a good effect size because you'd have something that's statistically significant but not practically significant for if any 320s are in here. But now let's go to the min of what I just created here. So we're going to look for the min of this, the min of the mins. Min of min. Min of mins. And yeah, it can do it. It can make, yeah, effect size. Yeah, that's a big thing in research is like a good effect size. And that's the practical significance of your model. So I've heard people saying they don't even publish p-values anymore because it can be deceptive. I mean, they probably, I would hope they'd still want you to have statistically significant p-values, but I figured they might just assume that. But I heard, it was a while back, it's like 5 years ago, it was like, scientific papers are no longer using p-values. And I was like, what? I can't help that people misuse statistics. It gets to me, but I can't help that people, it's just that if you misuse them, it's just, yeah, people don't do replications of studies. You can't find out that people are not misusing them. That's the problem, is that people could misuse them and then we don't have the safeguards in place to find out that the results they found were actually due to random chance. So, or more likely due to random chance. And that's how you replicate. Because you can find low p-values. It's not that hard to do. I just found a ridiculously low p-value because I generated ridiculous amounts. I just generated like 1 trillion numbers, not lying. I generated, how many numbers did I generate? We just generated, is that trillion? I think it's 1 trillion. 1,000 million, only 1 billion. Only generated 1 billion numbers. Only 1 billion p-values were generated, and that's the lowest one we found right here. Out of 1 billion random p-values. 1 billion. Which shouldn't, I guess I could have just done 1 billion. I think it's right. 1 billion. I guess I could just, yeah, run random uniform 1 billion p-values. So, but it's kind of, you know what's interesting? Watch this. If we do a hist of the min, we'll it actually, yeah. But do I have my plot window weird right now? When did I change the plot window? Oops. I gotta learn the command for this. It's par mfro equals concatenate 1 1. There we go. I finally learned it. I learned it. Oh, the p-values have that distribution? They're right skew. Whoa. That might be an F distribution. That's interesting. I did not know. Effect size tells us more about the association than the p-value. I don't see it. I don't know if it's a debatable point or not. Or except don't know if it's a debatable. Yeah, the effect size tells you more about the kind of contextual relationship. The p-value just tells you if it's unlikely by random chance that the difference you observed, like if the difference you observed or whatever you're looking for was unlikely by random chance. So the p-value is just a statement that this effect size is not likely by random chance. And especially the assumed effect size by random chance would be 0. And so you're saying with the p-value that's low, I have evidence that there is an effect. So if the p-value is low, it's like there is an effect here. The effect is not equal to 0. So the null would be that there is no effect equals 0. And then the alternative would be that the effect is not equal to 0. And so low p-value just gives you that bit of information. But then what is the effect size? And probably what would be better is a confidence interval on the effect size. Like I'm 95% confident the effect size is contained in the interval blank to blank. Anisha, great stuff right there. Yeah. Anisha, and you said are you PhD? I think you're PhD engineering, right? That's awesome if so. Because I'm sure they want to get estimates for what's going on and, not create bad models. So I like it. I love it when grad students are taking this class. They come in with a very unique perspective. So, and then they teach me things because I think, because we have 2 PhDs in this class. It's like, I'm glad I can teach you something. Glad I know something. Because you guys know a lot more than I do on a lot of topics. Public health. Oh, cool. Yeah. Well, then this right here, I'm sure a lot of research. And so Nitin is mathematics and great job on everything, because I know you've all been working so hard and learning how to code and learning the different models. So yeah, it's all just data. It's all being able to, manipulate and use data and finding out how this best works for you. So that way you can be like, okay, let me, run this model, let me visualize this data, let me understand what's going on right here. And I think it also gives you like logic skills. I think this class helps you logically think through like processes, because they always say like learning to code kind of helps you. It's like a puzzle. So it's like a logic puzzle, which I'm really proud of everyone. Everyone's working really hard. Test is out. But with that, I think I have some meetings today. I can't remember if my meeting's at noon or not, but I am going to head off. I think with the test and everything, everyone's pretty calm. I think the next assignments are coming up towards the weekend. 320 question. I'm confused on the wording for 3A. Are we just supposed to write the code, or are we answering? Which one is that, Emily? Is that the assignment or is that the newest assignment? Might be. Let's take a look. Let's hop over here to the courses. Oh, that's so cool there, Anisha. So yeah, we're talking about climate data on 320 today. And so yeah, assignment 6. Great job, Emily. Amazing work. Let's see what assignment 6 says. That's not assignment. That's notes. It's not assignment. Let's go here to assignment 6. Wait. A simple linear regression was done last night, right? I tell you, I was just like releasing that. There we go. Answers are out for those. And let's go. Okay, good. That's not out yet. So we just publish the answers, and I'll be posting the other answer ones. Didn't change the names of those, but that's all right. You're welcome, Anisha. Thank you so much. So packet 127, homework packet, page 127. Let's go there. Okay. Thank you so much for telling me which one it is. Open homework packet. Homework packet. Okay. Da-da-da-da-da. And here we are. So is it this one right here? I believe it's probably this one, because we didn't get to transformation today, but we'll definitely be talking about it tomorrow. So very confirmation bias. A very common transformation pair is the log-log, although it's not the transformation that gives the highest number 5. Boop. We want to predict someone's body fat based on their triceps. Predict and examine a 95% prediction interval, the body fat percentage when triceps equal to 18 and 31. So we got some really good notes from today, and I'll have to remember to put this online. So if anyone's looking, this should be under this section. We've got BAS 320. I need to start closing pages. BAS 320, good, I have the 17th marked. And this was done right in here. This is an important part of the code right here, where we're going to make a data frame with values, and we're going to make predictions. So we're going to use the data. I'll remember to delete this out. Body fat. And we're loading, that just loads the data, which is already loaded inside of reg class. And now we need a linear model, which we can go here. And we're predicting triceps from fat, right? Let's check. We want to predict someone's fat from their triceps. So we go here to fat. We go here to triceps. when we go here to EX3 body fat. Make sure these would not be in quotes because these are objects. They're not characters. They are objects. We make the model. Now we want to predict somebody's fat from their triceps. And I believe the values were 18 and 31. We have to concatenate this vector because it's multiple objects. And here we go. And we could show the predictions then. Be interesting to see how many people do this. There it is. There are the predictions right here. You could also use the function I built earlier, but here's the predictions for the body fat, and this is the prediction right here, Emily. This is the prediction for the person's body fat, and let me show the full thing. So if you look at the code right here, I loaded up the data frame. I created my linear model. I stored my variables that I want to make predictions on, and then the function right here, we'll just break it apart a little bit more, shows that we're going to predict on model M. We're going to use the new data here, and then the interval we're going to use as a prediction interval. You could do as a confidence interval. Oh, yeah. So which thing are you talking about, which number to use? Are you talking about, like, when you make predictions? So is it A? So this right here, if you want to examine 95% confidence and prediction intervals. So if you want 95% confidence and prediction intervals, you're going to have to do this twice. So we'll call this predict 1. And if you want both of those, you have to do this twice. Reason because you can't, as far as I know, run both of them. And so now this would be confidence. And we go here. And so there is the confidence, and then there's the prediction interval. And you could take, technically, you go here to type. This is overkill, but I mean, it'll make it look a little bit nicer that we can see. So let's rerun these. Oh, we want to put these before, though. I'll show you what this will do right here. This will put a column in there of that word. Oh, predict 2, where are you at? There we go. So now when I run this, oops. What did it not like? It got mad at me. Oh, because it's a list? Let me look at this object. Oh, man. Really? Well, this makes it not as fun to change. Hopefully I'm not going too crazy for the people watching. Let me see if this does it. There we go. Okay. So it was a list, and it got mad at me, so I had to go in front of this and go as.dataframe. So when we change this right here to a data frame, it can now take the object and turn it into a data frame. And you don't have to have it like this. This is overkill. Why is it 13? Oh. So this is the predicted fat for an individual with 13, 18-inch triceps. And are those the right numbers? Yes. So this is somebody who has an 18-inch tricep is predicted to have 13.93 grams of fat in their body. And right here, if we go to visualize model, let's visualize the model, and this will help us see what's going on. Great questions, Emily. Sorry, I just wanted to do that coding thing right there. If we visualize the model, we would say the person with 18-inch triceps, like let's go right here at 18, let's trace up, and then if you trace over, where does this red line hit? The red line hits right about where, Emily, for somebody who has an 18-inch tricep, and if you were to trace over, it hits right below what number? So the red line, if you go here and trace over, it hits right about where? Where does it right about hit? If you go up from 18 and trace over, the red line is where? And this would be irregardless of prediction or confidence. You go from up from 18 and then you go over. It's going to hit right about there, which where's that numerically? Right at 14, which is 13.93. And then if we do it for 31, which is all the way over here, you would trace up right here. And if I trace this over, where does this about hit, Emily? Where does this about hit? If I go from 31 and go up and then trace over, where does that about hit? And so this fit right here is the line. Does that make sense what this fit, Emily, is? That it's the line that if you were to go to 18 and then trace over, the line predicts about 14. If you're at 31 and you go up and then you go over, it goes to 25, basically. It's where the red line is at. So that's the fit, and the fit is the same irregardless of model. Does that help make sense of what Yes. Thank you for asking. And this is what I want, Emily. You're doing the perfect things right now. You're working on it. Something doesn't make sense. You hop in, you say, what does that mean? And then we're like, oh, it's the fit is the prediction. So this is the Y hat right here, which is this, it's the same Y hat regardless of which model you make, because the center right here is the same whether it's prediction or whether it's confidence. And so yeah, great questions, Emily. Great job. Great work. Where in the notes is examples for how to keep the values with as numeric or taking a mean with a class? Oh yeah, that's I can't. That's on the test or that's on the take home. I can't say, but it's definitely earlier on, Adam. Definitely check out. And good thing I'm glad you got the starter right there. So I can't. No, don't worry. The retract is all right. No, but you can ask these things. Then I say I can't say, which is fine. But it's definitely in there. Start, using Control F through the notes and seeing where it's at, and you should see it. So definitely Control F through the notes a little bit, and you will see it. So start, look at the key phrases you had and see if you see it. Good question, Adam. Very good question. 100 points, good question, but I can't answer it. I can say Control F is great, though. So I can't say which set of notes have it, though. But no, that's a good question. No, great job, Adam. Great job. And I'm glad. I wonder what it was, Adam. I'm glad the start of the video helped out. I figured that was the best way to say, like, okay, today I'm just going to show the process again. And then that way, like, you can see it and be like, okay, here's what I need to do. And then hopefully it looks like the disconnect was found. So I'm glad. Awesome. Well, I think I'm going to do some meetings here, and I'll be answering emails. I might hop on the Discord, say hey to everybody. But that's got it. We will end class here. Email me if you have questions. Say hey, and have a great evening, everybody. Good luck on the test. Email me with questions, and I will answer them. Talk to you later. Bye.